Perfect. All right. Hey, everybody. Welcome to our Flanders Scientific AMA with Bram Desmet from Flanders. He's the big kahuna over there. We couldn't come up with a good title for him. We have a great session. He's got a ton of things to show us, a ton of things to talk about. And as usual, because Bram is a wealth of information and the questions and answers can kind of go off the deep end, we're going to try and keep the questions and answering like a little bit organized if we can. So here's the agenda. I'll share it with you guys. So like as we go through things, if you have like a burning question, of course we can cover it, but try to keep the questions to like what we're talking about. And then at the end, there's just an open free for all. And that's where things usually get pretty deep. But I don't think you can stump Bram. So anything you want to ask him,
oh, I can definitely be stumped.
But that being said, Bram, it's up to you. Take it away, my friend.
All right. Well, thanks everybody for joining us for this. It's pretty cool to be able to get in touch with all of you, even when all this is going on. So as Jamie said, I think kind of what I wanted to do first was do kind of a 20-minute presentation or so on display technology, just kind of center our discussions and hopefully also kind of head off a lot of questions that may otherwise, come at different times and kind of make it more of a disjointed conversation. So just something to center ourselves around. And I will do my best to keep that to about 20 minutes. It's going to be on display technology kind of generally. I'll tie that into stuff that we're doing currently, stuff that we're looking into for the future, but more of a display tech rather than like a sales pitch or anything like that. So anyway, with that in mind, I'll jump into the presentation. If you have questions, probably best to try to flag Jamie down because I'm going to be paying attention to the slides and whatnot.
Yep.
And then Jamie can interrupt and if needed, and we can go from there. So I am going to share my screen and hopefully that works. And I hope everybody can see that. Everybody see a monitor, Lizard?
Yep.
Yep. All right, cool.
Yep, looks good.
So basically, this presentation is a modified and updated version of one I did for the SMPTE Atlanta chapter last spring on display technology. So we won't go back too far, but I think as context, it helps to, let's start with color television and start a little bit with some background info that kind of puts things in perspective, I think. So one of the first color televisions that was kind of commercially available was the RCA CT100, which is pictured here. The reason I picture it is because what's really cool about this is that this actually did have essentially an NTSC 1953 color gamut. And you can see that that's pretty darn wide, actually, even way back when. The issue with this is that it was extremely dim because the phosphors were not very efficient. So what that ended up meaning was that you had to really watch it in a very dark room to be able to see it, but it did have great saturation. The really dim image was a huge problem, which is how we got to SMPTE-C, EBU phosphors, P22 phosphors. All those phosphor sets were designed basically to get us brighter images. The SMPTE-C phosphor set, which eventually became the SMPTE RP145 standard, is actually, that was developed by Conrack and RCA back in the 60s. So very, very old technology, really, but became kind of the de facto standard for North America, at least, as we got into the 80s and beyond. You could do about 80 to 120 nits on these, so they're way more light output. You can actually watch them in environments that weren't necessarily completely dark. Now, of course, there are all sorts of other CRT type issues, like geometry, linearity, convergence issues, those types of things. But the main thing you see here that I was trying to point out is that you do have a really narrow color gamut, which gave us those kind of orangey reds. If you ever tried to, on a CRT, look at a Coke can, it just never really looked that Coca-Cola red. So things kind of evolved in 1990. We actually had the introduction of Rec 709. It's been around longer than a lot of people realize, but that was kind of the introduction of that. What that helped with, at least, was that had some standardization going forward between Europe and North America. We didn't deal with EBU phosphoresets and SMPC phosphoresets and P22 phosphoresets. There was kind of an agreed upon colorimetry, although interestingly enough, there really were no CRTs that could do Rec 709. So we had a standard, but not really the displays to do it. That kind of evolved in the 90s and 2000s to get us to LCDs and plasma displays that could basically do Rec 709. So it was nice in terms of color consistency. Program material could be moved from North America to Europe and whatnot, and we had very similar, at least the potential for very similar looking color, but still a very narrow color gamut. And that kind of brings us to where we are these days. So we've got displays that have gotten wider and wider color gamut. P3 color gamut is relatively common on higher tier displays. They can do all or most of P3 color gamut as their widest color gamut. And UHD and 4K, of course, are a lot more ubiquitous than they used to be. And monitors like our own XM551U and 651U large format OLED displays, the 55 and 65 inch units, are pretty typical representations on the professional side of this type of kind of status quo in displays right now. They're really well suited to SDR viewing and SDR mastering. You do see a lot of these OLEDs used for HDR home viewing and maybe client viewing even, but they're not actually that well suited for HDR viewing, and we'll get into that a little bit. I know they're relatively widely used, but we can show why they're typically not considered suitable for mastering applications for HDR content. So now that we've got wider color gamut and relatively high resolution, the question is, what do display manufacturers and TV manufacturers do to make people buy more TVs? And so the thing we can do is kind of the quest for these better pixels. There's diminishing return for higher and higher resolution. Lots of testing has been done on that. Unless you go to very large format, 75-inch plus displays, that advantage visually for the typical home viewer from 4K to 8K is pretty marginal. So resolution really isn't going to be the thing that is going to help us. On the acquisition side, it's certainly great to have higher and higher resolution, but for displays, it's not necessarily where you're going to get serious gains. Where we can get some real performance improvements are in color gamuts and higher luminance displays, so that we can go to things like HDR. But with color gamut, we have to be a little careful. So I think that the color gamut improvements that you'll see will actually be relatively small and incremental from the current point, from P3 onward. And part of that is because of some of the unintended consequences of things like Rec 2020. So if you look at Rec 2020, the primaries actually lie on the spectral locus on the outside here. Those are essentially single wavelength light emissions. So what you get there is something that's really more the domain of laser projectors, and it's not particularly well suited to flat panel displays. It's hard to get to those primaries with flat panel displays. And even if you can, and this is something we've learned from the people who have made laser projectors, is there are other problems that you run into. So one of them is you get increased observer variability, or what's called observer metameric failure. So as the basically primary get narrower and narrower, you have more and more disagreement between observers on exactly what it is they're seeing. So what some laser projector manufacturers have found out is that by broadening out those primaries, basically instead of going to 1 nanometer kind of spectral emissions, that's what these lines are here, for the primaries. These are basically the Rec 2020 primaries, these lines. They broaden them out, and by broadening them out, they reduce that issue. They also tackle other projector specific problems like speckle. But one thing that helps with a lot is reducing this observer metameric failure. So even if we could do all of Rec 2020 on flat panel displays, we might not want to. For that reason, I do think we're going to still be in a point, kind of like we are now, where Rec 2020 may very well be kind of a operational container, but not really a operational used color gamut of actual display technologies. So we will probably get wider gamut than P3, but with no real standardization between P3 and 2020, I'm not sure there's much to be gained from wider and wider color gamut beyond where we are today. So where does that leave us in terms of, again, things that display manufacturers can do to make displays more appealing, to make the image better? We can try to increase the overall color volume. So we can take these wide color gamuts that some displays are already capable of, and we can mix in higher luminance, higher contrast. And that really is what's going to provide the most potential for wow factor and for, again, improvements in display technology. Because of this, the demand for HDR is really shaping what both semiconductor manufacturers, TV manufacturers, and actually professional reference monitor manufacturers consider either viable or desirable kind of display development efforts. So the future success of things like OLED, LCD, micro LED are all going to be tied really closely to their ability to address these HDR requirements. And displays that are not well suited to addressing HDR, those technologies are going to go away. So with that in mind, kind of looking at some of the display technologies out there. So I know most of you know and love top emission RGB OLEDs. And that's an emissive technology that has absolutely phenomenal black levels, so very, very high contrast. You can make HDR versions of this, but it's really not well suited to it. Now, if HDR had never come around, and I think even if you had asked most of us 5 or 6 years ago, what will be, you know, kind of the continued kind of top tier display solution 5, 10, 15 years in the future, because we all loved our OLED so much, we would have probably said OLED will still be kind of the champion because nothing can beat it. But the reality is that that ignored this kind of HDR necessity and how well suited or not these displays are for HDR. So one of the biggest issues, of course, is you get massive amounts of burn-in with these OLED technologies. And that becomes significantly worse as you go to higher and higher light output, generate more heat, and have more rapid aging of these displays. Aside from that, these displays typically also exhibit a lot of loading behavior, so it's very difficult to do large areas bright. You can do small areas bright, but as you fill up your entire screen with bright content, you tend to have this kind of automatic brightness limiting that happens on these displays. So it's relatively difficult to meet these kind of current and future HDR requirements with that technology. So even if that technology had stayed with us longer than it had, long term, it probably would have gone away or kind of become less favored because of its inability to address HDR requirements in a way that kind of satisfied the market and also in a way that was affordable. Now, that being said, there have been some attempts to make OLED technology in general more appropriate for HDR, to make it more efficient and be able to get to brighter light output in more efficient ways. And that's where we get this kind of WOLED technology. So white OLED, WOLED, you hear it referred to those things. Those are the panels that are basically made by LG Display. They're used in a lot of consumer televisions from LG, from Sony, from a lot of different companies, Panasonic. They're what's used in R55 and 65-inch units as well. And the way that they achieve kind of higher light output is this kind of boost channel, this additional white channel. Now, what's important to realize about the way the technology works is that at any given time, only 3 of these 4 subpixels are on together. So you're never driving all 4. And That leads to some pretty big challenges, and is part of the reason we get this kind of fundamental problem when it comes to mastering quality HDR capabilities out of this WOLED technology. For home use, you can get away with it because you can do tone mapping. You can go to, you can do a 600 or 700 nit output. And if you have issues, they can be masked a little bit, or they aren't as important to the home viewer. For mastering applications, it becomes problematic because of this type of behavior. You get what is essentially a volumetric collapse. So what that means in a more simple way is, if I want to do a specular, glint off of chrome, or a headlight at night from a car, and it's relatively neutral, it's basically essentially a white light, I can probably do that relatively accurately with this technology and with this white subpixel kicking out a lot of extra light. But what we cannot do is very bright and saturated together. So what that means is if you have like a very bright green or red or blue LED light or something like that, it won't be shown accurately. You can either preserve the saturation or the luminance, but not both with this type of technology. And that's why these are normally relegated more to client monitoring, SDR monitoring, in professional applications, or for home use. As much as I kind of harp on the inability of these things to do HDR in a professional context, at home, it's what I use as well, because it does give a great picture, very good black levels, and they're very economical in terms of their actual cost to the end users. But for mastering, this is a huge problem because these displays are not purely additive. And what I mean by that is the red, green, blue channels together don't give you that white light. It's actually a combination of this white with any two other subpixels at a time. So because of that, you have this kind of strange behavior, but which does limit the viability of this for mastering applications. But in addition to that, you also have burn-in concerns still with this. Because of those burn-in concerns, and because of this kind of non-additive behavior and this volumetric collapse, people are left kind of searching for actual mastering solutions that are appropriate for HDR. One of those that's of course become rather popular as of late is what we call light modulating cell layer. It's what you also hear referred to as dual layer LCD. And what this does, just as a recap for those not familiar, is that you have a backlight that is essentially always on. It's always kicking out max luminance. And then you have a traditional LCD layer on top. So you get your red, green, and blue basically filters. And then sandwiched in between those layers, you have essentially a monochromatic LCD. And that's the best way to think of it anyway. That light modulating cell layer is essentially a monochromatic LCD layer. And those two layers are roughly 1,000:1 contrast each, but they kind of have a multiplicative effect when you stack them on top of each other. So you get effectively 1,000,000:1 contrast, black levels that are just about as good as OLED. You get no halation, no flare, no loading behavior, importantly, unlike OLED, you can do full screen 1,000 nits or very small area 1,000 nits. It's not a very complicated device in terms of driving them. There's no complicated backlight algorithms or anything like that. So from an operator standpoint, they're really easy to use. They look great, and they, again, don't have a lot of those other issues. Now there are, and I should also mention, this is what's actually used in our XM311K, and our 311K has pretty much become our most popular HDR monitoring solution when budget isn't really the main consideration. So if money is no object, this is the solution people go to because it works really well. It's very simple. No burn-in on these either, which is another huge benefit compared to OLED technologies. The downside with this technology is that if you want to do over 1,000 nits, it's very difficult to do. You're going through two layers. The backlight always has to be on over the entire screen. That means it generates a lot of heat and it draws a lot of power. So if you want to try to crest over that 1,000 nit threshold to get to brighter and brighter HDR, they're not particularly well suited to that at this time. So when 1,000 nits isn't enough, or if cost is a factor because these are still quite hyper expensive to make. What else is there? Well, this is why we're seeing such a prevalence of zone backlight technology. So dimming backlights are going to be here to stay for quite a few years. You're going to see more and more companies releasing these. They'll come in two flavors. You'll basically have your global dimming, and you'll have your full array local dimming. The full array local dimming is typically considered the higher tier option, but with any full array local dimming option, the quality of the image is going to come down to two main factors. One of those is how many zones do you have. A system with 128 zones is going to perform considerably worse than a system with 2,000 or more zones. The other thing is the algorithms that drive the behavior of the LCD and the LED backlight working together. The better the algorithm quality, the better the display will perform. To that end, the XM310K in our lineup is a unit that uses such a full array local dimming. It has over 2,000 LED zones. And that display can actually do 3,000 nits peak luminance. It's one of the brightest commercially available HDR monitors out there, 1,000,000:1 contrast ratio. And what we've done, as we've seen that this is likely going to be something that is used more frequently in the future, is we spent a lot of time taking feedback both from colorists and from some of our professional partners who have pretty big stakes in the HDR game. And we've taken a lot of their technical feedback and we've tried to improve the algorithms on those. We actually just wrapped up a 6-month project working specifically on optimizing the full array local dimming behavior, not just for the 310K, but for potential future projects as well. And that is, if you haven't seen, and nobody has because of quarantine, if you haven't seen an XM310K in the last week or two with the latest firmware, it's really worth taking a look at. We were pretty happy with it the way it was 6 months ago. I'm really thrilled with the performance now. It's gotten even better. The new peak mode on this is quite impressive. So again, that kind of speaks to the fact that algorithms are a huge part of what drives the potential quality of this, because we've always had 2,000 zones, but the performance has improved significantly just by tweaking algorithms over time. So again, I think you'll see more and more technologies with full array local dimming. You'll see variable controls for those. That's one thing that we're kind of big fans of, is we give you the ability to operate in a static backlight mode. If you're just using SDR and you don't want any sort of zone backlight behavior, you can do that. If you want to use it in SDR with zone backlight, you can do that. If you want to use it in HDR with zone backlight, you can do that. And if you want to change the type of algorithm being used, we basically give you 3 different modes: one optimized for peak, one optimized for motion, one optimized for contrast. Peak is, I think, with the new improvements we made, what people will use 99% of the time. But if you look at a lot of the consumer options, they kind of lock you into one type of algorithm, and there may be certain shots or certain scenes you get to where an algorithm just kind of falls flat. It doesn't perform as well as you would like. Giving the ability to change those settings is pretty huge, and we think an important part of making this more viable as a technology. I think what you'll see with full array local dimming and with global dimming is that the cost of these will eventually come down pretty sharply as there's wider and wider adoption on the consumer side as well as the professional side for these types of technologies. A few more slides to go. So there's 2 important trends in the LED backlighting that's behind those light modulating cell layer and zone backlight. Global dimming, local dimming, doesn't matter. But the 2 huge things that have changed in the last few years are that in order to do wide gamut in the past, you basically needed individual red, green, and blue LEDs. And that was a huge technical challenge because those aged at different rates. And so you'd have faster color shift on those units. Also, it tends to affect viewing angle, actually. So we'll have a color shift in one direction as you move left and a color shift in the other direction when you move right. Now we have these wide gamut capable white LED backlights, one of the most prevalent being PFS phosphor. PFS phosphor is essentially what's behind the latest 1000 nit light modulating cell layer units. All of them are essentially using that type of backlight technology, which again uses white lights to get us to very wide gamuts. So that's a huge performance improvement, makes them much more stable over time, makes them very wide gamut, and provides pretty darn good off-axis viewing as well. The other trend is, and you'll be hearing this, and this will confuse the market at large for sure, is you'll hear this term mini LED used all the time. So mini LED, on the semiconductor side, there's actually thresholds for what's considered an LED, a mini LED, and a micro LED. Mini LED, the way that you'll see it on the market in the next few years, that's all going to be backlighting. So those won't be true direct view displays. But when you hear that term, it just means that instead of hundreds of backlight elements, you're going to get thousands of backlight elements typically. And again, what we've seen is the more backlight elements you have, generally the better the performance is. I will say that given that, in theory, the more backlight elements, the better. I actually went to CES this year though, and the one display I saw on the floor that was claiming 16,000 zones was one of the worst looking ones out there. So you have to combine this still with very good algorithms to get good performance. But this is an interesting development. These higher and higher densities will get us better and better performance. And at some point, there's also kind of diminishing returns as you add LED elements. And that's something I think is important. You don't really have to get one-to-one to get something that looks a lot like one-to-one. Especially with human vision, you tend to get veiling glare and things like this when you are looking at very, very bright lights. So if you have a 1000 nit pixel next to a black pixel, it's hard to tell if that zone is slightly smaller or slightly bigger that's driving it, because you get this kind of natural veiling glare in your eyes from that bright light source. And one potential hybrid solution, there's actually a consumer TV manufacturer that's already implementing something like this, and I think you'll see this from other people in the future, is the combination of full array local dimming and light modulating cell layer. So we take basically, imagine a Frankenstein monitor that combines the XM310K and XM311K. And you may be asking yourself, why in the world would anybody do that? But the reason is for that luminance limitation that we were talking about, right? So you can, if you imagine a system that uses full array local dimming and light modulating cell layer, you can get something that kind of allows you to go extremely bright while minimizing halation and flare a lot more than you could with a single layer. And on the consumer side, I think what you'll see is very low backlight density. You'll probably see, like 128 zones or something like that. And so you can still get halation, you still get flare, but the halation and flare will be greatly reduced compared to a single layer panel. On the professional side, there's an opportunity here to use higher density full array local dimming backlights with this front panel. And what remains to be kind of seen is, one, if anybody actually does this, but I think they will, and two, if they do this in just one mode or if they do it in a couple modes. So on the consumer side, this is basically probably going to be something where you always have full array local dimming working with the light modulating cell layer, and there's no static mode. It's always going to do both. But you could imagine on the professional side, you might be able to set something up to where you have the backlight always on for 1000 nits, and you can do 1000 nits edge to edge, and you don't use any local dimming whatsoever. So you have no potential for artifacts, no potential for any of the kind of display issues that you might have with local dimming. But then let's say, you do that for your day-to-day work where you need 1000 nit monitor, but then let's say you're asked to do a 4000 nit project. So that one-off 4000 nit grade where you suddenly wish you had a local dimming, full array local dimming monitor like the 310K instead of a 1000 nit monitor like the XM311K, you can switch it into this kind of two-stage mode, and this two-stage mode would enable that full array local dimming and allow you to get, not full screen, but you get smaller areas, the specular highlights, to maybe be 4 times brighter than they would be in the static mode. So this is a real interesting concept. Like I said, there's already a consumer TV manufacturer doing this. There probably will be more than one professional manufacturer doing this. And this may very well kind of become the top tier solution. This is probably going to be expensive to do, so I don't think that you're going to see this in production monitors right away, but I wouldn't be surprised to see this on the on kind of the high-end post side in the coming years. So why is everybody kind of scrambling to do all these different types of options? Well, because we all know that micro LED is kind of the great promise, and that's what we hope we can get to, a direct view system with very, very small LEDs. The problem with this is that you need over 25 million distinct LED chips to make a 4K TV. It's very expensive, very difficult to manufacture, hard to scale, and there have been a lot of reports of issues with trying to manage colorimetry accurately on these. That being said, this has the potential to become the gold standard when it comes to displays. But you're probably looking at, for the type of sizes that we would use in kind of day-to-day production or post-use, probably something like 3 to 5 years. Now, that being said, there are micro LED solutions already out there. If you went to CES, you would have seen a bunch of large video walls that were using variations of micro LED technology. There's also very small scale micro LEDs being used in like 1-inch displays and smaller. So this stuff is out there, but scaling it to 25-inch monitors in a cost-effective way is probably going to take some more time, which is why we're going to have a lot of these transitional technologies. And even if we get to the point, you know, say 5 years down the road where everybody has access to these micro LED displays, that doesn't necessarily mean it's going to be the winner. Something I've been grown very cautious of, I've been doing this since 2005, and my dad was in this industry back to 1983 selling monitors, so I've really grown up around it. And what I've seen over and over and over is that the best technology doesn't always win out, right? So if you look at top emission RGB OLEDs, you look at plasma displays, you look at CRTs, at any given time, the professional industry lamented the loss of those technologies and couldn't understand why the best thing out there performance-wise was suddenly no longer available. But it happens over and over and over. So just because this is the best performance-wise potentially doesn't mean it's necessarily going to win out. So some of these other technologies could be with us for a very long time. And what that means for all of you is that you should not expect that any one technology will become the only kind of gold standard out there. You're going to have a myriad of options for many, many years to come, all with their kind of pluses and minuses, with mini LED light modulating cell layer having the advantage that they got this huge head start. So those technologies, by the time micro LED comes around, may be so darn affordable, so commoditized that it might be hard for micro LED to really gain the ground it needs to become, you know, the technology out there. So that's the review of kind of displays, all the things that we're looking at, working with currently. And I think if anybody has questions specifically on this stuff, I'd be happy to talk about it. I've also got monitor calibration demos coming up after this, but for now, if there are questions, this might be a great time for it. I'm gonna stop sharing my screen and go back to me. And I didn't read any of these questions on the side, so I don't know if there's
Yeah, we'll go through them. Chris Bolton has a question first up.
We were just rambling on in the background. We like to do that. So any of you have been on these chats the last couple of days, I always ask the same. I'm starting to ask the same question over and over again. In your opinion, based on a 25-inch type monitor or something very close to that size, what would you see as sort of enough contrast and enough nit output to be a viable on-set HDR monitor?
Yeah, that's a really good question. I know there's been a lot of kind of sales pitching to the idea that you can get away with 500, 600 nits, something like that. But the reality is PQ is an absolute scale, right? So if you want to see the highlight detail between 600 and 1,000, you need a monitor that goes to 1,000, just plain and simple. Now, if you're willing to compromise, you can do things like tone mapping. You can do things like soft rolling your HDR highlights, but then you're no longer really in a reference mode. So, you know, it depends. Do you need to see that detail or not? Maybe not every monitor does, don't get me wrong, but I would probably say for anybody who's handling it kind of seriously, what you want is you probably want at least that one kind of hero monitor on set, if you decide you want to monitor HDR on set. And then everything else can use, you know, a tone map or look at a log image or something like that. That's fine. But yeah, that's kind of my take on it, is if you do want to see those details, you need that monitor.
Thank you.
Cool. Thank you. Curtis Abbott, you're up.
Oh, I think you're muted. Sorry.
Yeah. What, along that same vein, what is what's the HDR preview on the DMs? What's it doing exactly?
So it actually has a couple different modes. It's a really great question. So going back to Chris's question, you know, what's enough, right? It comes a lot of times scene dependent, right? So you could have a system, for example, that's taking log and then converting to PQ and giving you PQ to monitor. And if you're doing a dark interior scene, but you happen to be monitoring PQ, but you got, you know, your APL's, you know, 20 nits and you have highlights going no more than 200-300 nits, you may want one type of HDR preview mode that works well for you versus another. So what we have on ours is two different modes. We have a soft roll and we have a hard clip. What the hard clip does on the DM monitor is basically hard clips near the peak luminance of the monitor. So on a DM250, about 300 nits. So it will show you 0 to 300 nits in the hard clip mode, 0 to 300 nits of that PQ scale, code value represented absolutely accurately on screen. But then anything over 300 nits, you just lose. It's hard clips. Then the soft roll, what it does is it basically tracks along PQ perfectly up to, this is from memory, I think it's like 125, 150 nits. And then starting at 150 nits, it actually does a soft roll of all the details. So it takes all the code values that would represent values from 150 to 10,000, and it squeezes them in that 150 to 300 with a tone map. Not dissimilar to what a consumer display does. It's, you know, not Dolby Vision level tone mapping. It's very rough, but what it does is it tries to give you some more highlight detail, so you can see at least that there's information there. It's not being represented one-to-one, but it is showing you information there. I will say that we were one of the first to have this type of HDR preview, and the HDR preview we have on these was basically built around 1D LUT transforms. If you want something even more accurate, or maybe not accurate, but even more pleasing, there's a way to do this with 3D LUTs as well, and we can help you with that process. But you can actually use a program like Lightspace to profile your monitor in a high luminance output mode and actually do a 3D LUT tone map system. That wasn't available when we first had the built-in feature, but if you want that, it's something you can build very easily for basically any lower luminance monitor. And what's neat about that is you can kind of choose, depending on what your scenario is, how that tone mapping works, right? So you may not want to preserve, like we do with ours, we try to leave room so you can see every code value up to ones that represent 10,000 nits. But if you're only going to be, you know, if your PQ, log to PQ transform is only going to 1,000 nits, then you don't need to waste reserving some of those code values for the 1,000 to 10,000 nit range, right? So you can actually get more detail in the highlights by saying, all right, just build me a tone map that goes from 0 to 1,000 nits and tone maps it into a 300 nit display. So you can do these types of things. You know, again, they might be good for other people on set. I wouldn't use it as your primary master in an HDR monitoring scenario. But if you need all your other displays to kind of look in the ballpark of the HDR reference master, if you don't have the ability to send those log, if you need to send them or Rec 709 transforms or whatever. If the only option is to send everything on set PQ, then you can use, you know, DM240s, DM250s, DM170s with those preview modes or with the 3D LUT transforms that I mentioned to get something that looks relatively close. Certainly anything below 300 nits is going to look pretty damn spot on. It's really the stuff over that that's not going to look quite right.
Cool. Thank you, Ryan DeWin.
Hey, Brum, thanks for coming out. Quick
No
question. Can you tell us a story about how we arrived at the Judd modified color matching function? We were using, you know, the old 1931 for a while, but when the switch came, I guess I'm asking a question about the history. What problems does it solve? And yeah, how did we get here?
So Judd-Voss modified CMF has been around way longer than OLEDs. The implementation of it is a point of continued contention. So basically, give you the high level overview. What ended up happening was we had these OLED displays come to the market, right? And the OLED displays had fantastic contrast and people loved that about them. There's a fundamental problem though. You calibrate this using standard CIE 1931 color matching functions, and you calibrate to the same you know, standards as CRT monitor. You plop it down next to a SMPTE CRT, and all the facilities looked at this and went, they don't look the same. What the hell's wrong? So, and because CRTs were the gold standard, the automatic assumption was, well, the OLED is screwed up. So how do you fix that? Well, you can perceptually match it, but that doesn't sound very scientific, right? So some clever engineers basically tried to figure out the root of the problem, found out that it was actually fundamentally an issue of predicting accurate metamers. And so they looked for color matching functions that would be more appropriate for dealing with the spectral distribution of OLEDs. So Judd-Voss was selected after some testing. I believe the testing was actually done in conjunction with Minolta. So they did some testing and found that that was a color matching function that would offer better visual matching to the CRT. The way they came up with the actual values, because everybody's like, oh, calibrate to Judd. Well, to any color scientist, that sentence is nonsensical, right? But what they did is they used the Judd modified CMF to go through this process. First, they set up a CRT using CIE 1931 color matching function to proper D65. Then what they did is they switched their measurement gear over to using a different color matching function. So in some software and even in some spectros now, like the CR300 actually allows you to load in different color matching functions. What they did is they loaded in different color matching functions to the spectro, and they measured that CRT, and they found how that CRT measured at white in Judd. Then what they did is they calibrated the OLED, again, still in Judd modified CMF, to be the same number as the OLED. Then they switched back to CIE 1931 CMF on the spectro, and they measured the results on the OLED, and that Judd modified equivalent match in CIE 1931 gives us the figure 30673180. Those are not the numbers in Judd modified CMF. The Judd modified CMF numbers are completely different. But if you do that match within Judd modified CMF and then measure the OLED when you're done using CIE 1931 CMF, you get 30673180. Now, if you know anything about color matching functions and the way spectros and calibration works, there is kind of a fundamental catch with this, is that we've only done the white balance. So the whole industry was like, all right, well, we're just going to calibrate to this other white point, and we've kind of done this really rough white point adjustment, and it made most people happy. And so, you know, a few companies before us, and then we jumped on the bandwagon too, because it became kind of the industry practice, said, all right, we'll do that. But we're not really using Judd modified CMF to do the full calibration. If we were doing that, it would actually impact the values we read everywhere, not just the white balance. So that also means that there may be ways to do even better perceptual matching. You could actually use a spectro to calibrate, to basically measure one display and then use that as a reference, and then have the other one calibrated to match all values, not just white balance, within that alternate CMF. The other thing is that Judd modified CMF is kind of a halfway solution. It works for a lot of people. It improves color matching for a lot of people, but for some people, it actually makes it worse. And part of the reason for this, and I have there's like an hour-long boring science presentation on our website with this if you want to see it. But it talks about how these kind of ways that we see things differently, these metameric failures, vary a lot by age too. So typically older observers see OLEDs a certain way, younger observers see them another way. So this kind of difference of opinion on the way things look breaks down a lot of time by age. It's not always by age, but overwhelmingly there is an age bias, and it has to do with the aging of the eye. I hope, does that make sense? Yeah.
It does. And I wonder, that has nothing to do with the revision of D65 turning out to be, I think I was reading somewhere that there was a revision of Planck's law in physics, and that changed it changed it to what is it, 6,504.
Yeah, so it's I think it's 6503.6 or something like that.
Right, like that's unrelated, right?
Yeah,
or
so no, it's unrelated, but it does point to another interesting thing, and this is kind of just nerdy tidbit for everybody, is that this is something that drove us wild when we were evaluating different spectros on the market. So we get two spectros that read, in their native software, or if they had a built-in readout on them, that would give us the same exact XY, but it actually spit out different color temperatures. And we're like, well, how is that possible? We have the same XY and luminance value, and then the color temperature values, because there's different ways to calculate color temperature. And that kind of speaks to what you're talking about. So you'd get like this 15, 20K difference in color temperature. And it was kind of maddening until we remembered our color science and why that was the case. And they were just using different equations.
Awesome, thank you. Chris Bolton has another question.
Yes, sir.
Color space conversions. It's sort of back to my original question again. Sorry, don't mean to hit a.
No, go ahead.
But another question we sort of generally ask is for a 25-inch size type monitor, does it not make sense not to go 4K and to stay in sort of an HD resolution realm to give us bigger pixels? It might be a little bit less money to produce a monitor that has more advanced type HDR and colorimetry without the resolution?
Yeah, so it's an extremely logical question, because you know the natural assumption is that it is going to cost more to go to 4K. The issue comes down to, that is the case if we talk about the hyper expensive way to develop a monitor, which is to develop the backlight independently from the front panel. That's not the way 99% of the professional reference monitors are made. We typically, in all of our current products, we have purchased complete assemblies, right? So the backlight assembly comes with the front panel assembly. And the issue is that, at least on in other markets besides this one, 4K and HDR kind of go hand in hand. So while those are obviously separate things, people who are willing to pay a premium for HDR typically are expecting 4K as well. So the 4K advanced panels with, whether it's light modulating cell layer or whether it's zone backlight, those complete modules are available to us, whereas the HD versions aren't. So we could build an HD version, but a lot of times building those elements separately is more expensive, especially because we'd be doing them at such low volume than just buying the complete assembly. So that's one of the reasons you're not seeing that more. It's not to say it can't be done, it's something I know us and some other manufacturers have. As we get to zone backlight being more and more of a thing, there are manufacturers who are jumping into building their own backlight units because it gives you greater control. We haven't done complete assemblies in something yet, but we've built portions of it, drivers, other things, and it's certainly been on our radar to do more of this and not. I can't say too much, but yeah. So yeah, but that's the reason. To your question, that is the reason you're seeing that. Why the hell is someone trying to sell me a 4K 17-inch monitor? I can't see the damn difference, because the 4K unit as a package, the backlight combined with the front panel was probably less expensive than trying to build your own HD version, and your own HD version wasn't available on the market.
Right. So it's just the volume of tooling kind of thing.
Yeah, and it's even little things like the backlight's the hard part. Just be perfectly honest, like binning LEDs and like doing that is you want to know why a Pulsar costs what it costs, or actually why you can't buy one, is because of that. Binning those elements, building backlights, that's the money pit. That being said, again, with it being kind of clear that zone backlight systems are probably here to stay for a while, I think you'll see some manufacturers jumping into actually trying to build these. The problem being that when they do, it may, and the end result may still be, it may be better performance, but it may still be more expensive. So yeah, it's tough. I know that a lot of people are like, well, I don't even want to try to deal with 4K on set. So I totally get the question, but that's the reason.
Awesome. I got a question for you, Bram. Two parts. People were asking in the chat about the Apple monitor. There's two different, I guess, options when you order it, like the nanotechnology and then the other one I forget. But people are going to inevitably try and use that for post applications, and maybe hopefully not, but on set. Can you talk about that panel, if you think it's good, or if you think it's just the first step to getting consumers that direction?
I don't want to talk too much about specific companies, also just because of who some of our customers are. So
Fair enough.
But suffice it to say that generally speaking, again, going back to what makes a good zone backlight system, the more zones you have, typically the better something operates. So something with 500 or 600 zones typically is at a huge disadvantage to something that has 2,000 zones. And there's also a relationship between the zones and the actual physical front panel resolution as well. So there's only so much you can do with algorithms. So you typically, with less zones, are going to get more halation, more flare. And then the designer of that display has to kind of decide what it is that you do as a compromise, right? So you can either allow for massive amounts of halation or flare, or you can dim those peak highlights when you have small, bright objects. And not talking about specific displays here, but generally speaking, that's the behavior you'll see, is that you go to a small enough bright object and you'll actually get that object not being bright anymore. Or you'll see massive amounts of halation that wouldn't be present in something with a higher backlight zone count. So just, yeah, that's kind of my general take on it.
And then secondly, do you guys have a good example? I was asking this yesterday with Bill Freitner, but do you guys have a good example of when things fall apart, like what to keep an eye out for, like the halation that you're talking about? Like, is there a good list of the problems so that people can know to look for those issues?
I can send you a
visual
photo
examples.
that sums it up.
Yeah,
I can send you
examples would be awesome.
I don't know if I should share it. I'll share it privately with you later, okay? I have an image that showcases it really well. And
well, it doesn't have to be that one issue, but I guess I'm talking about the whole range of HDR issues that different displays and different manufacturers are coming up with kind of workarounds. And it'd be interesting for us to show people like DPs or directors, like, hey, this is an issue, keep an eye out for that. So visuals always go a lot further.
Yeah. So one of the difficult things with that is a lot of times that stuff ends up having to be simulated because it's hard to put in perspective. And even the image that I'll share with you later, one of the issues with that is that the halation that's present in the lowest backlight zone count display looks a lot worse in the photo than it does in real life, because in real life, the veiling glare you get from 1000-nit object staring you in the face kind of cancels out that effect. You don't see the halation nearly as much, which is why a lot of these consumer TVs also get away with only having 128 zones. You or I might catch it. The average observer probably isn't too bothered by it. And it's especially with moving video, it's a lot harder to catch. It's easier for your brain to kind of excuse that. So when you're dealing with a static image, and if you're a colorist, or even worse, if you're doing VFX and you're trying to rotoscope something in HDR, then you're going to notice halation flare pretty badly.
Right. Okay. Great. Does anyone have any other questions about Brahm's demo before we move into monitor calibration? Of course, you guys can, if you come up with them later, we can always ask them at the end part of the session. But if not, we'll move on to the monitor calibration demo. And we're going to try and keep the questions to a minimum just because of how dense this topic is. But I think we're starting off with lightning LUT examples, right, from both vendors?
Yeah. So, yeah, we're going to start with quick profiles, because there's no lightning LUT in Lightspace. But yeah, we'll start off with quick profiles. Then in Lightspace, then we'll go to lightning LUT in CalMan. Same concept. What we're going to showcase is that when you have a very linear display that behaves in a that predictable way, you actually don't need to do these massive profiles to get excellent results. There is a time and a place for massive profiles, but I just want to showcase a little bit those differences. And actually, I'll share my screen, and just to sum it up as we start, so you know what I'm kind of driving at. This is we'll do Lightspace first, but this is kind of the example from CalMan. So this is a lightning LUT versus a lightning LUT, and everybody can see my screen, right? Sorry. Yes.
Yes.
All right. So lightning LUT versus a massive profile. So you see that the results are essentially the same for this particular type of display. So one of these took 2 hours to perform, the other took about 6 minutes. So the question for you is, do you spend that extra time to get that max error down from 1.4 to 0.8? Average error is actually the same. So certainly, I think for production applications, time is money, and if you don't have the time to do those 2 hour calibrations, especially if you have multiple displays to do, those quick calibrations can work quite well. So I will.
Hey, Bram, real quick.
Yes, sir.
Just wanted to make a note about this. Guys, whoever couldn't make like the Able Cine class that Bram and I did on calibration, we spent some time discussing, like, can we push lightning LUT, which is in CalMan, and then the quick cal, which is in Lightspace, as like a viable option if we have 4 displays or 2 displays to quickly calibrate our monitors, as opposed to doing like a 2 hour or 1 hour pass per monitor. That time really adds up. So just so you guys know, the difference that we're comparing it to is like a full 3000 patch test solution, compared to, I think it was like 141 test patches, right?
Yeah. So what I'm going to showcase to start is actually kind of the extreme end of one of these scales, which is 24 test patches, and we'll see what type of results we can get, and that's going to be using Lightspace. The CalMan example, yeah, that's 141 test patches in the lightning LUT process versus doing 3000. So all right, so I've got Lightspace open. I'm going to use Resolve as my test pattern generator because that's pretty darn ubiquitous, and it's free, and it's easy to use. So I've got Lightspace open. I'm going to make sure I have my probe selected. I have the CR100 is the probe that I'm going to be using. I'm going to go to Resolve. Now, one thing to note in Resolve, if you want to use it as a TPG, you have to have content on your timeline. So a lot of people end up, opening Resolve, starting a project, and let me actually share a larger portion of the screen here, because otherwise you won't be able to see this. So they'll go to Workspace, they'll go to Monitor Calibration, they go to Lightspace, and then it won't work. And the reason it won't work is because you do have to have content before you can connect. So in Resolve, with content on the timeline, you go to the color tab, you go to workspace, you click on monitor calibration, and you have light space. It's going to ask you for an IP address. You get this IP address by basically starting light space. We're going to go to the calibration interface. I'm going to hit OK to connect to my probe. I don't need to sync right now. Go to Network Manager, and this enable control basically turns on its ability to communicate with Resolve. And the IP address is actually going to be the one listed here. So 10.2.11.55.6. Going to go back to Resolve, hit connect, and I'm connected. One important thing here is, I'll actually do it. Don't hit enter. Drives people crazy. If you hit enter after you type in the IP address, it actually closes out the dialog. If this dialog closes, your connection terminates. It trips up a lot of people. So just hit connect and leave that window open in Resolve. You're going to go back to the program. It says enable. You can select what patch size. We're going to use full screen because we're just using an SDR cal here. Hit close. And then if you want to test it real quick, you can basically use this slider to generate a test patch. And I will actually, real quick, I'll show you. I have a monitor set up in the room here. So you can see that basically I move my slider and I get a response on the display, so I know that it's working. Share screen again. And there we go. So back to Lightspace. So I'll start here. There's two ways to do Lightspace cals. There's the calibration interface and there's display characterization. Calibration interface was originally more for evaluating displays, kind of doing validations. Display characterizations is what traditionally was done to do volumetric characterizations and then build LUTs from that. What's happened though is that with a lot of linear displays, you really don't need to do a lot of measurements. So you can use these really short, quick profiles as they're called, and you can actually just build your LUTs from that. So that's the example we're going to have here. I will actually go to the monitor again, just so I can show you what you're supposed to be doing on the monitor before you start. So I've let the monitor warm up. Really 30 minutes is plenty. That's probably more than you need. I'm going to put something on screen here so it's a little bit easier to see the menu. And then I'm going to control the monitor. So the first thing you're going to do is on the monitor menu, you're going to go to the color management menu. And you're just going to go to LUT bypass, and you're going to bypass the 3D LUT. That essentially turns off the volumetric calibration and gives you a neutral starting point for profiling the monitor. You're essentially profiling the native behavior of the monitor when you do that. So now that my display is set up correctly for the profiling, go back to Lightspace. Maybe. Yep, okay. So I'll go back to Lightspace, and I'm going to go to options. Sorry, there we go. Let me control my screen. One moment. There we go. I'm going to go to options. Now I'm connected with the CR100. The CR100, if for those of you that have that, has a few different sync options. You can do an auto sync, a manual sync, or no sync. Don't do no sync, it will fail on you. For auto sync, what it will do is before it takes a reading, it will actually measure the frequency response of the display, and then it will take the reading. And it will do that before every single reading. That slows down your calibration time a lot, so it's better to use a manual setting. If you do the manual setting, you can actually do something called probe calibration, where you'll measure the screen and it will actually measure the refresh rate. But you see when I do that, it's going to give me a really high number here. So it gives me a really high number because it's basically measuring the PWM backlight. The way, and that will work, but the better way to do this is actually set your sync to the frame rate of your source. So I have a 24p timeline here. I'm going to set 24. What this does is actually, it actually kind of averages readings or averages exposure over several frames and actually gives you more stable results. So that's kind of a cool shortcut to get better results, is just type in the frame rate here, and that will give you better overall results and save you the trouble of having to do the actual probe calibration sync part. You do want to select the correct matrix. Matrix creation, if you have a spectro, you can do it yourself. If you don't, you can, if you have a colorimeter, you can actually send your colorimeter to us. We'll create a matrix for free. You just let us know which FSI monitor you're using, and we can create those matrices for you. And we use, sorry, let me turn that off. And we use a CR300 now. It's a 2 nanometer spectral bandwidth spectra, one of the best you can get on the market. That's what we use to create our matrices for your colorimeters. So I select that matrix, I hit OK, and now we'll get to the actual profiling part. So of course, if you're familiar with it, you've already done all those things before, you wouldn't have to spend much time on any of that. And then all I'm going to do is hit profile here, and then I can select the different types of profiles. If you have a very linear display, typically you can get away with something as small as a gray only. So a gray only will actually just measure red, green, blue, and then it will measure about 21 points along the grayscale axis. I'm going to hit start. I'm going to give this a name, and I'm going to start this with Z so it shows at the bottom of my list because I have a lot of profiles saved on my computer. Let's see, DIT, and I'm going to hit OK. And now basically test patches will be generated. You'll see the slider move up here. It'll take readings, it'll profile the display, and it will give me a characterization of how that display responds. So the difference if you were to do a display characterization where you take 3,000 or 5,000 readings is that you're measuring a lot more points. So you're measuring more volumetrically what the points are. And that becomes important if you have less linear displays. We talked about those WOLED displays a little bit earlier. Those, especially at HDR levels, tend to behave relatively nonlinear. At SDR levels, they mimic linear behavior a little bit better, but it's still not quite perfect. So more readings helps a lot on those. Whereas more readings on something like a DM240, a DM250, you're only going to get a very marginal benefit by taking more readings because the display handles in a very linear, predictable way. So you see that, oh, sorry, move that window back. So you see, well, see maybe, I don't know why Zoom does that. Sorry, it keeps moving the window on me. All right, so you see that that calibration or that profile only took 42 seconds. So not very long at all. And you see the result here. This is the native gamut of the display. So you see the display is actually an extremely wide gamut unit. That's again because it's using PFS phosphor backlight. So now that I have this profile, I can close out of this and I can go to color space conversion. And this is basically what builds my calibration LUT. You'll notice that this is not kind of a hold your hand process as much as something like CalMan is. So it is a different approach. It's a very flexible approach. So it gives you the ability to do some things you can't do in other programs, but it does mean you really have to kind of learn the program before you use it. So in Lightspace, the source is actually going to be what your target color gamut is, right? So Rec 709 is what I want to calibrate for. So you see when I select that, it types in the XY coordinates for red, green, blue, types in D65, 3127, 3290, and it defaults to gamma 2.4. I can change any of those values if I want to target something custom or target a different color space. And then the destination, the best way to think of destination is where you're loading the LUT, and where you're loading the LUT is on the display. So I'm going to select that profile that I did. It's down here. And then I'm going to give this a name. Save yourself some trouble. Type in the name for the position on the monitor you want to save to. So if you want to save to user 1, call this user 1. If you want to save to Rec 709, call it Rec 709. So I'm going to save this to Rec 709. So I'm going to call this Rec 709. Peak chroma is a good default to use. If you're dealing with a display that has a smaller gamut than the target. So if you were, for example, with this display, it has a native color gamut that's smaller than 2020. you might want to use one of these other options like fit space or map space. If you're doing some HDR monitors, this hybrid selection is really good. There's a lot of information on the Light Illusion website on what all these do. But generally speaking, for these kind of plain Jane, large gamut monitor down to Rec 709, P Chroma is a good way to go. So I'm going to use P Chroma. I'm going to hit Create New. And now it's doing the actual calculation of the 3D lookup table. If you've taken a lot of readings, if you have a very nonlinear display, this can take quite some time. On this display with as few readings as we have, this shouldn't take very long. So we'll just wait a moment while this builds the 3D lookup table for us. And once that's done, we can load it to the monitor and then we can test the result. So you see here, the color space conversion report says that we're 100% within gamut. That obviously is because we have a very wide native gamut, bigger than P3 color space monitor, and we're just going down to Rec 709. I'm gonna hit OK. What's neat about Lightspace is that you can kind of open this and see what your 3D lookup table is doing. So it's taking you from this native gamut of the monitor down to this Rec 709 target space. I'm gonna hit File, Export, and then you see all the formats it can export in. I'm gonna export in the one appropriate for this monitor, which is Flanders Scientific 17.cfe. See, we had that name well before our friends at Colorfront. And then I'm gonna hit exports, and I'm gonna save this into my CalLuts folder, which I created for this. And now my LUT is saved there. So I'm gonna go to that file, Rec 709. I'm gonna hit copy. I'm gonna plug in the monitor. It's going to show up as a mass storage device. I had some saved in there earlier, so I'll get rid of those. And I'm just going to paste that file in there. With that done, I am going to go to the monitor. I'm going to go to the feature that says Update LUT on the menu. Hit enter, say yes, I'd like to upload that file. File's done uploading. And once that's complete, the last step is to basically go back to LUT bypass none. So the LUTs are turned back on now. And I'm gonna go to Rec 709, which is where I saved it to. And now I can use Lightspace to also validate my result. So what I'm gonna do is go back to the calibration interface. And this is where you can also choose how you want to validate. So we could validate with gray only, but that's kind of cheating because it's actually, sorry, let me share this screen again so you guys know what the heck I'm talking
quick question.
about. Yes, sir.
Somebody was asking, how did you connect the monitor? Is it over USB or Ethernet?
Yeah, so the all of our AM, BM, CM, DM series monitors, basically anything HD resolution, are connected over over USB. That's the USB mass storage that I was showing. So you plug it in, it shows up like it's a thumb drive, and you just drag and drop the files on there. So very easy to do. On our XM series monitors, this is actually slightly different. We actually have a network interface, and you can actually directly upload from within Lightspace or CalMan. You type in the IP address of the monitor, tell it what color space you want to save to, and it automatically saves it over a network connection. So a little bit different of a workflow there. That's something we've wanted to do for a long time, but we just, wasn't supported broadly on all of our hardware. But with the XM series, we've decided to go that way, and it does make uploading files even faster and easier.
And how are you controlling the menu remotely?
I am controlling it with the IP remote utility, which I think you guys can see now. So I was using that, and because we have shortcut keys, I was actually able to do all of that from my keyboard. So up, down, enter buttons are basically the 4 arrow keys. You can also do this from Stream Deck, obviously. If you have a Stream Deck, you can use it to control the hotkeys within our IP RU application as well.
Thanks.
And let's Sorry, let me, man, Zoom windows drive me nuts. I need a.
Oh, if you go to view options when you're screen sharing, you can hide the floating panel.
Few options. Actually, all right, that worked. I don't know. All right, so
do you have time for a quick question as well?
yeah, go ahead.
And Michelle Delormier, you're up. Make sure you unmute
Hey,
yourself.
Brian.
Hey,
Am I unmuted? Hi.
Yep.
you are unmuted.
Hey,
We
so
hear you.
if you had selected Judd Voss
Mhm.
earlier in the probe calibration settings using a matrix from you guys, would we
Mhm.
deselect that now and go back to 1931 for the profile validation?
Yeah, so there's a couple different ways to do that. So one of the nice things with the with Lightspace is that if I go to manage here, actually not manage, sorry. If I go to the LUT creation, tell you what, let me do the QC validation real quick. And after I do that, I'll jump to, because it's in a different window, I'll show you how you can actually set up a standard to validate against Judd modified, if that's okay. And then that'll better answer your question, I think. So to validate what I just did, so we can exit out of this, what I'm gonna do is, sorry, go profile again. And I can do these different kinds of validations. The memory colors with secondaries is kind of akin to like a color checker. So I'll do that one. That takes more readings, so 45 readings to validate the results. I'm gonna call this Z validate. So it's at the end again and hit OK. And this is actually gonna go through the different readings and kind of validate the calibration of this DM240. And when that's done, I'll kind of show you how there is improved graphing and reporting now in Lightspace. That was kind of traditionally one of the things that people pointed out as a wish list item with this program, is that they would offer better kind of quality control reporting, and they do have that built in now.
Hey,
So
Brom,
once
would
this
you
is
talk about the importance of like validating before calibrating? Or the necessity of it, like sometimes if you just validate and your targets are still good, you don't need to
yeah,
calibrate.
I mean, so yeah, that's what I would always do before I waste time calibrating anything, is see if it needs to be calibrated. So that's when you can do basically this process before you even start, and you can check how your display is calibrated. And when this report is done, I'll show you just a real quick and easy way, after you do this kind of memory colors and secondaries check, a way that you can quickly see if your display could benefit from calibration or not. So obviously the color gamut response looks excellent. Memory colors are gonna look spot on in the graph I'll show you in a second. But the one I jump to as a real quick and easy kind of determination of where my display lies is this delta E distribution. So what this shows you is it shows you delta E ITP, delta E 2000, and DE 1976 all in one graph, and a left-weighted graph is good. So basically what this shows you is the percentage of values that are DE between 0 and 1, between 1 and 2. So you see here, everything is, 72% probably of our values are between, 0 and 0.5. So really excellent calibration results with a very, very quick cal. So again, I can get much better results. Well, much better. I can get better results if I do 3,000 measurements, but is it worth your time when you have something that turns out this well already? Probably not. But what's neat is I can go down to this manage, go to Z validates, display, and you can actually now see how these memory colors line up versus these targets. So you can see that we're hitting all those targets kind of right where we want to be. We have a good solid calibration. And if you want, you can even export this to a PDF and print those reports as well. And that does quite a good job. Back to Michelle's question. So what you can do here is you can basically create any custom target you like from within this color space conversion window. So we'll give that a second to pop up. And
Hey, Bram, I'm not sure if my question was clear, but it's more about the probe
the probe,
offset.
yeah. Okay, cool. Let me get to that. So if we wanted to do that alternate target, what you would do though is just go Rec 709. Now you could type in like 06, oops, 0, and again 06. So you could type in a custom target here, and you could save it and give it a name. So you could do like Judd Voss, whatever, if you want to create a custom target. But what you were asking about was on the options for the probes here. Is that so?
Exactly.
Okay, so where were you? Yeah, sorry, just elaborate a little bit. I'll try to answer the question.
So it's under monitor type, like a reference type. I think under reference probe display presets. Is there a Judd Voss there? No.
No. So what these are for is if you are so if you have a probe.
I just have I think I have an older version of Lightspace than this is showing.
Okay.
So
Gotcha.
I import my matrix into that matrix box, but then under a setting close to where it says calibration settings for you is a place to select OLED and whether to choose Judd Voss or not.
I haven't seen that in any recent versions of Lightspace. But let me explain quickly what these do, and then hopefully we can figure out where is it. And you are using Lightspace, not Calman, is that correct?
Correct. Yeah.
Okay. So the active probe and reference probe, for those interested in that has to do with if you have a probe where you cannot load in the matrix onto the probe body directly, you can actually do it within software. So any matrix that I save here from a spectroradiometer determined matrix for my colorimeter, if I was using something like an I1, I could actually load this as a file or manually enter in this information. So what my active probe reads for red, green, blue, white versus what my reference probe measured for red, green, blue, white. So that's a software-based way of doing matrices. I greatly prefer if you have a probe that can store it directly, doing it as a matrix here is what you want. The Judd Voss part probably wouldn't come up here unless you have multiple reference profiles, Michelle. So I'm not sure if that's where it is that you're thinking of.
If you click on probe calibration, does it pop up? That like
no, probe calibration is strictly going to be for sync.
Okay, maybe I just have too
what?
old of a location for doing this.
You're using an I1?
Yeah.
Okay, so what you I know what you're. I think I know what you're talking about now. So the reason we don't see it is because of the probe I'm connected to. So when you're connected to an I1 has different default positions, and you can actually build software-based matrices with any one of those as a baseline. So the answer to your question is you need to know where the matrix is built from. So if we built it on the generic position on the I1, then you'd want to use it, your matrix information with generic selected. If we built it on top of the one that was OLED, you'd want to select OLED. So it really depends on what we used when we plugged it in here. And if you're unsure, let the support guys know. That's something they take note of, which of those settings was used when they were doing the matrix creation. But essentially what that is on an I1, you can't save onto the memory of the probe. It's not end user accessible, but there are several generic positions loaded by X-Rite from the factory. So they have like an LCD selection, they have an OLED selection, I believe. There's a few different selections. And all of that is kind of a moot point for us as long as because we're creating a software-based matrix, but we do need to know what starting point you had on the probe, whether it was generic or OLED or LCD or whatever it may be. So best to check with the people who made your matrix, what they were using at the time the matrix was created.
Okay, so
sense?
I guess then the question is, does it stay in that same position when you go back to validate?
Yeah, so all your any probe settings that you set here are essentially sticky throughout use of the program. And if you exit the program without crashing the program, it should remember those settings when you reload the program as well. The only time settings are kind of lost through cycles of the program, to my knowledge, is if the program were to crash out. But typically those settings are remembered. So for example, my matrix selection of DM240 was still active when I opened the program because it was the last thing used. So the program remembered that. So yeah, that should all stay sticky throughout. If you select it once, then it should stay as you move through validation, profiling, anything like that.
Except then it's different between like my DM250s, my CM240, my BM210s.
You do need to change
Each of those is a different
matrices.
matrix. Yeah.
Each
Okay,
of those
got
is a
it.
different matrix. Absolutely. Yeah. And that's a real important point. Colorimeters are not display agnostic, right? So if you're measuring with a colorimeter, your results are in essence only as good as the matrix you're using and the spectra that was used to create those matrices. And do remember that monitors drift, but probes also drift. So if it's been 5 years since you've had your colorimeter calibrated, definitely send it in for new matrices. Those ideally should be redone every year. How necessary the timing of that is depends a lot on the particular colorimeter you're using. Some are way more stable over time than others, but it depends a lot on if they're using glass filters or if they're using gel filters, if they're well sealed or not. But all probes drift, so they do need to be recertified and recalibrated.
Thank you.
Yeah, no worries. Sorry that I was I don't use the i1 enough personally. It's really the support team who's more familiar because they build all those matrices for people. But I'm usually using the CR100 or the CR300, which are a little bit faster as well. All right, so that's the light space profiling. Does anybody have questions on light space profiling, light space characterization, anything like that before I show how this is done in Calman?
Yeah, Chris Bolton has a question.
Sure, Chris.
Yeah, Kyle's got his hand up before me.
Oh, sorry, Kyle, go ahead.
Hey, what's up, Bram? Quick
Hey.
question for you. Is there any variances between like DM250 panels or all the different panels when it comes to spectro matrices? Like, for instance, is it a better workflow to use your matrix that you probe than it would be for me with, like, say, a CR250 to pull my own matrix? And then should I matrix every DM250 I come across, or is it better just to keep one and use that as our baseline?
Depends. How picky are you? So so generally speaking, the spectral distribution of something like a DM250 doesn't change too drastically. That being said, as panels age, especially on panels that have independent red, green, and blue light emitting channels, which is the case with OLED, it is possible to have slight variations in SPD. Now, those are typically not going to be significant enough to cause a real perceptible issue. But if you have a spectro available anyway, making a matrix doesn't take much time. You can do it for every unit. I mean, that is definitely a best practice, and it will only make sure that your displays look even more similar. If I were a DIT and time was precious to me when I wasn't in quarantine, I certainly wouldn't spend the time making. I would make one for all my OLEDs and just call it a day, because it's going to be more than close enough. Where you may get into this becoming more of a real world consideration is, again, on something like RGB top emission OLEDs with independently aging channels. If you have one unit that's brand new and one that's 7 years old, there may be just a little bit of a perceptible difference if you don't do it. And if you have the time and if you have the equipment, there's no harm in doing it that way. It will only improve consistency. It won't hurt consistency to do it, to do extra matrices.
Awesome, thanks.
Yeah, no worries.
Oh, Chris Bolton, you're up.
Well, the funny thing is, I totally forgot what my question is now. Oh, you know what? You know what it was? My question was in sort of the 5K US price range. If we're going to go out and buy a probe, what would be your suggestion?
CR100, hands down. They are phenomenal probes. They're very stable over time. And if you send it to us, we can make matrices very quickly and easily with them. They actually have a really cool CRI utility that allows you to make matrices very quickly. But then once the matrix is created, we found that the CR100 is the one that is the most stable. So it's the one that requires recalibration the least. A lot of other colorimeters are excellent because they're very fast. They have very, low light, very good low light capabilities. There's some probes that measure a lot. K10A, for example, measures faster than the CR100. But the CR100 we found to be the most stable of those. It provides excellent accuracy, and colorimetry research is very quickly becoming kind of a standard throughout Hollywood. I know a lot of large facilities who are heavily invested in those probes. So that would be a good way to go. And as a bonus, it looks like a lightsaber, which is always awesome. So.
And which version of Lightspace CMS works with that probe?
Basically anything from Lightspace FSI Pro and up from there. With Lightspace, it's best to look at their website for the breakdown of different products, or our website if you're just looking to use it with our monitors. With our monitors, there are FSI specific versions of Lightspace that are lower cost but only export in our LUT formats. So there's Lightspace for FSI that only works with an I1, very, very inexpensive. It's $600 for the program and the probe. There's FSI Pro, which I think is around a grand, and that will work with the K10A, CR100, and then of course you have full versions of Lightspace. LTE, you have LTE, you have a Pro, you have XBT. Depending on what you need, how many different display technologies you need to deal with. But anything from kind of that $1,000 version up typically works with the CR100.
Yeah, I have your I1 OEM version.
Yeah, so with that, something important to mention, this is true of CalMan and Lightspace, is they both have upgrade paths that are pretty reasonable. So if you have the FSI version for the I1 and you want to upgrade, just contact us and we can get you a custom price quote through Light Illusion for upgrading from one to the other. You won't have to pay, full sticker for the new version. It basically just a new license you load in. And they're really good about offering fair pricing on those upgrades.
Great.
Cool. More Lightspace questions?
You had a question about Lightspace.
Hi, Bram. I don't suppose you've been one of the beta or alpha testers for the forthcoming color space. Is there? If so, is there?
Yeah, we actually showed early iterations of color space at the last NAB and at several trade shows. We've been an early tester of very early alphas, and yeah, so we've had extensive experience with what's been available so far. I still need to check the latest version. Steve just sent me that yesterday. I just haven't had time to go through the latest iterations, but yeah, we're pretty familiar with it.
Okay. Is there a significant difference in terms of performance on basic stuff like what you just showed?
On the basics, I think the fair answer right now is probably no. The engine gives very similar kind of performance results. I think one of the big things you see now is going to be the different visualizations and the different layouts of the program. It definitely looks like a much more modern program now. And I do know that in the future, there will be some significant additional updates to kind of the engine driving generation. But the value, I think, is going to come in where people are able to do more of these kind of volumetric analyses of display performance. Because right now, we're all kind of relegated to the same thing, right? We look at things like color checkers, where we check a handful of memory colors, and we check gamma response, and we check color gamut, and we call it a day. The 3D visualization of color space kind of allows you to look at error by region in the display, and it kind of identifies the strengths and weaknesses of different display technologies. So we think it's a pretty cool tool from that visualization aspect. But there's a lot more coming with that. So I think it's going to be in terms of actual calibration accuracy or performance, it's going to be a little bit before we see significant differences between those.
Okay, thanks.
Just to clarify, is color space something that's like a module inside of Lightspace?
No, so so basically Lightspace has been around for quite a long time. It's been taken about as far as it can on the current framework. Color space builds on a completely new framework, and has, at least in theory, the long-term ability to hopefully go cross-platform finally, which I would love for a calibration program to actually run natively on a Mac. So it's not going to do that right away, but the new code base is more flexible, more modern, and allows for some of these new visualizations. If anybody wants kind of a private demo of color space, I'd be happy to do like a Zoom session with you and show you some of the different visualizations. But the 3D visualizations of color gamut, or color volume, I should say, coverage are really kind of compelling. You have little like error vectors that show you the degree of error. It's pretty slick. It's definitely something worth checking out.
Awesome. Any other questions, or can we move on to Calman? I think we can move on.
All right. So I will close out of Lightspace and we will launch Calman by now Portrait Displays.
They're in Seattle, aren't they?
Yeah, believe so. Yeah, in Washington area.
Yeah.
So we'll wait for that to load. I think, kind of fundamentally, one of the differences with Calman is it definitely is a more, whereas Lightspace is a very open architecture that allows you to do a lot of very powerful things. It doesn't hold your hand quite as much. Calman definitely is a more workflow-based approach where it guides you on do this, then that. And for that reason, I think Lightspace, once you become kind of a pro user of it, can be a little quicker to operate. Calman can be quite quick too if you skip all the steps you don't need. So once you get used to how the thing works. So, but they're both excellent. Both have very good calibration accuracy. And again, we'll kind of showcase how that works here. So, so I've got the workflow that we've built, which is just a FSI calibration workflow. You'll see that I'm already connected. I got sync mode to auto. I'm going to change that to on. This is kind of the similar method to what we did in Lightspace. I know that my frame rate of my source is 24, so I'm going to type in 24, and that's going to provide good measurements with the CR100. You have your matrix selection here. So all the matrices that have been programmed in, select the DM240 matrix. And on source, I'm going to do find source, and I'm going to select resolve. Now, before I do that, I should mention that the way that, if you're a first-time Calman user, you would normally do this is you'd go through the workflow and you'd hit next. And then you can do all these same things from within kind of the workflow window here. What I see is that a lot of advanced users, once they get used to this, just kind of skip all that and go right to the top where you can make these same selections very quick without moving to different windows. You connect here, again, 10.2.11.55.6 is my IP. I'm going to go up here. I'm going to go to workspace, monitor calibration, SpectraCal. Still says SpectraCal, but look for the Calman one. And you're going to hit connect. And same thing as when we were using Lightspace, is going to now be talking to Calman and generating our test patches through Resolve. So you can go through all these steps here where you kind of do your pre-cal measurement, your, you know, 1D LUT, 3D LUT, luminance check. There's all these different things. If you want to do the equivalent of what we just did, if you're kind of a, again, a pro user and you want to just get to the nitty gritty of doing your 3D LUT already, you can skip ahead to the Cal 3D LUT. I'm going to do the same thing with my monitor. I won't switch to the monitor feed because you guys can probably still see it in that small window, I believe, if you have it over to the side. But
yep, we can see it.
All right, I'm going to see here, and there we go. And I'm going to just bypass the 3D LUT again. That's all I'm doing on this display. So LUT bypass 3D. So the 3D LUT is now bypassed. I'm going to move my IPRU out of the way again. And then from here, size the window so it looks a little better. From this 3D LUT calibration, I've selected CR100, I'm bypassed. I'm going to hit the Auto Cal button. And first I need to select the display, sorry. So for our Box IO device and for the XM series, you would select Flanders Scientific. But for any of the other things, you're actually going to select SpectraCal and you're going to select the cube generator. And so this is the cube generator 3D LUT. That'll basically generate the file that we need to load to the monitor. I'm going to hit connect. And then from the formats, I'm going to select Flanders Scientific, CFE2, because that's what this monitor requires. So CFE2, that's correct. And then I can choose where it's going to save this. And I'm going to save this again to my CalLuts folder. Now that's set up, I can go to AutoCal. And when I go to AutoCal, you see all these things confirmed again. I'm saving in Flanders CFE2. I'm going to select other models. I'm going to type in DM240 because that's what I'm calibrating. And this is where you select what the file name will basically be. So, and where you want to save it on the monitor, user 1, user 2, user 3, Rec 709, SMPC, all those positions available on the monitor. If you don't want to overwrite the factory calibrations, both with Lightspace and CalMan, we recommend saving to the user positions first. And then if you find that you're happy with that result, you want to override the factory result, you can save it to Rec 709. I'm going to save this one to user 3. And I'm connected to Resolve in video range. So I'm going to select video range down here. And then for the cube calibration settings, calibration type, sorry, this is where you get to the different types of calibrations that can be done, right? So lightning LUT is what we're going to use, but if I wanted to use a longer profile, I could go to something time-based. So I tell CalMan I have, you know, an hour to spend, so I'm going to move my slider to 60 minutes, and it'll basically take as many readings as it can within 60 minutes and give you the best possible result based on that. You can also do a point-based. So if you say, I know that I get good results on this display if I use 3,000 measurements, you can basically enter in any number up to, I think, 10,000 readings, and it'll give you a time estimate as well for how long that will take. So if I want to do the large profiles, that's how I would do that. But we're going to do lightning LUT to showcase how that works well on a monitor with very linear behavior. And once I have those things set, profile path, so CalMan traditionally had, let me actually go back to that, that's important. So this is where you set your targets. So I'm going to be calibrating for Rec 709 with Gamma 2.4, and I'm in video range right now. So if you want to change targets, if you want to calibrate for JUD, if you want to calibrate for P3, you would actually do it from this area here. And if you want to do different, EOTFs, you could type in your EOTF value or select your EOTF value from here. So that's what's going to set your targets. So something that they added several years back, which is pretty convenient, is that you can now retarget. So you can actually load a previous profile, and let's say you want to do one profile and calibrate for both, 2020 and Rec 709. You actually don't have to profile twice. You could do that from the same profile data. So that's useful if you plan on doing that. You can select a profile path where you can easily find that data. But we're just doing a lightning LUT for Rec 709, so we'll keep everything nice and simple. I'm gonna hit OK. And now it's gonna start taking my readings. And you'll see that it will give us kind of a countdown timer here, telling us how many readings are remaining. And once that's done, it will automatically generate the LUT into the folder that we selected. And then we can drag and drop that onto the monitor, update the LUT, and do the validation. So once that's done, we'll show the validation. I know I rushed through some of that, but this will take a little bit of time as we're doing about 90 some odd more readings. So if anybody has any questions in the meantime, now would be a great time to ask them.
Luke Taylor has a question.
Go ahead.
Yeah, sorry. I was just trying to figure out how many patches do you run on those bigger LG-based panels you guys sell?
So for the SDR cals, we actually run a 17 by 17 by 17 profile. So that's going to be 4,913 patches, I think, if my math is right. So that's in addition to also doing an initial grayscale profile. So we do a baseline back 1D 2.4 gamma LUT on those 1D LUT, and then we do a 3D LUT, and the 3D LUT is based off of about 5,000 readings.
Yeah, okay, thank you.
Yeah, you're not going to get away with lightning LUT on those, unfortunately, if you want very good volumetric behavior.
And that has to do with the actual, like, that additional, not pixel, but like the Z axis or whatever,
yeah, it's because you have that white, red, green, blue. So it's what I call a non-additive display, and that's kind of shorthand for non-additive for white. So most displays, if you're displaying white, that's just a combination of the red, green, and blue channels. On that one, though, white is going to be a combination of that white subpixel and then two others. It tries to mimic an RGB additive behavior at the panel level, but it's obviously quite complex and not perfect. So you need lots of data going in to give you a better volumetric result to basically account for all those kind of non-linearities in the behavior of the display. They can be calibrated quite well for SDR. Again, it mimics the RGB additive behavior close enough to where with 5,000 readings, you can get a great result. For HDR, that's a much bigger challenge because of the volumetric collapse on top of that. So they can be calibrated for HDR, but it's not easy.
Okay, and Jamie, can I throw one more question out there?
Yeah, go for it. Real quick though, hey Bram, can you switch your screen share to the monitor real quick, just so in the video we can see what it's doing?
Yeah, sorry.
And then Luke, go ahead. Yeah, then you can switch back after it's done.
So yeah, second question is, I wanted to just ask sort of like, what are some of the major challenges when it comes to calibrating for HDR? I mean, I've never done it, I've never been in a position to do that, but like time-wise, like, what are the challenges to expect with that?
Yeah, so there's a lot of different challenges based on the type of display. And that's probably the biggest thing that comes into play with HDR is that the approach is a little bit different for every type of display out there. So with WOLEDs, one of the huge challenges is that you can't do full screen patches, right? Because there's really significant loading behavior. You're going to get maybe 140, 150 nits full screen. If you go to like a 1% window, you can probably, depending on whether you have a consumer set or professional set, on the professional sets, you can get close to 1,000 nits. So because of that, because you have to use those small windows and because they're HDR level and because it's OLED, burn-in's a really big concern. So you can't really do a 5,000 point analysis without burning a nice little square into your monitor. So you have to kind of get creative. We recommend those displays primarily for SDR where you can use full patches. We do have HDR calibrations built in, but just to be very frank on our approach on that, what we did is we basically sacrificed a bunch of panels and did very large profiles in HDR to characterize the behavior. We use those as our baseline volumetric cal, and then we only calibrate the 1D LUT component because we can do that quickly enough to not burn in and damage the screen. And then we update that 1D over time as the unit ages. And that does a reasonably good job. I mean, you're going to get the volumetric collapse anyway, so you're never going to get the type of HDR accuracy that you'd get over like something like an XM311K or XM310K. So we find that that does a good enough job for kind of the client monitoring applications we typically see people use those displays for. So that's kind of the approach on those. With all of the HDR displays, you also have to think a little bit about whether you're using a 1D plus 3D or just a 3D LUT based approach. With the 3D LUT based calibrations, currently we only use light space. This is something SpectraCal, or not SpectraCal, Portrait is working on, and they will have 3D LUT based PQ output working well, I think later this summer. But right now, light space is what we advise for that, and what we use on something like our 311K to do those calibrations. And with that, you have to think about, do you have your back 1D LUT set up your baseline of the display in PQ, or do you have it set up for a gamma EOTF? On the 311K, we actually use a gamma EOTF on the display, and then we build the PQ component with the 3D LUT volumetric calibration. On the 310K, it's a slightly different approach, and that has to do with the way the algorithms drive the unit. The baseline EOTF of the display is actually PQ, so that changes the way the 3D LUT has to be built. So those are kind of complicated things. They're, we can walk people through those if they have those specific monitors, but it does kind of highlight that the approach is different depending on the display technology. Is it zone backlight? Is it light modulating cell layer? Is it WOLED? Is it RGB OLED? All of those displays kind of necessitate different approaches. And it's honestly been one of the big headaches with HDR is that you have to do all this research and find out what works well. So that finished, and that was a 6-minute calibration. So I'm gonna show that here. So you see here, 6 minutes, 10 seconds, 101 readings were taken. Hit OK. And now that will have been saved to my CalLuts folder. And I have user 3. So I'm just gonna copy that over. I'm gonna plug the display back in. This is the USB that I'm plugging in. So again, it shows up as a mass storage device. And I've copied that file. I'm going to go to this, drag that file there, unplug from the monitor, and now I'm going to update the LUT on the monitor. So I'm just going to go, and I can go to update LUT. Update LUT, yes. Okay, so the LUTs are updated. Going to go bypass back to none. I'm going to go to the top of the color space menu and select user 3, which is where I saved it. And now I'm going to validate that result. And that's where this post-cal verify comes in. And I'm going to select read series. And now it's just basically going to see how the calibration was. It's going to do EOTF check and a volumetric check. So right now it's doing the EOTF check. It's basically measuring the grayscale, and it's giving me my delta E 2000 values across here. It'll spit out the grayscale average and max performance. And then for the color performance, when we start measuring the color checker, which is kind of like that memory colors and secondaries in the other program, you'll see that that will be highlighted here as a summary as well. So you see here, max error on grayscale was 0.9, average is 0.5. Now we're going to do our volumetric check. I'm going to see how that
Are those
performs.
numbers good, Brom? Just for the people that don't know
when
this,
the graph looks broken, it's good. So with Delta E 2000, typically anything 1 or less is considered not a discernible difference. The normal threshold that is, as an industry, kind of usually accepted for SDR is as high as 2.6.
Would you show how to change that scale for the Delta E on there? Because right now it's set to 10.
Oh yeah, so what you can do is you can actually right click and hit properties, and you can actually change the access. So now we're going to do auto access. You can also do a manual access if you want to set like the top end as 5, you could do that, and it will change the scale accordingly. So that's how you change that scale.
So if you're seeing any values that are over 2 on that Delta E 2000 graph, that means perceptually by eye, you should be able to see a difference.
So here's the thing with Delta E, is it really depends on the color in question, right? So Delta E 2000 is not perfectly perceptually uniform. No Delta E metric is. Delta E 2000 is typically considered better than some of the older metrics. But what you'll see is that it really depends on the color. So a value of 2 on a dark blue is not the same as a value of 2 on a mid gray. The actual ability of an observer to tell the difference it varies depending on the specific patch in question. So these are approximations at best. The other thing that comes into play is, you have to remember the human eye is extremely good at comparative judgments. As an absolute measuring tool, it is absolute garbage. So if you put, something with a color difference of Delta E 1.1, and you have those two things butting up right next to each other, you might very well be able to tell the subtle difference. If they're on 2 displays where you have to turn your head left and right to see the 2 different displays displaying the different patches, you probably think they look the same. So it's very, very hard for your eye to be, kind of an absolute instrument, kind of like colorimeters.
We have time for a couple questions.
We do. So just as a summary though, max error 1, average 0.3. So again, the question is, do you want to spend 2 hours doing 3,000 measurements if your display can do this in 6 minutes? Probably not. So,
and that's specifically for DIT's onset, not in a perfect environment, like in a dark.
Yeah, even there. So
studio.
So here's my thing with that is that if time is no object and you can let it run overnight, then doing a massive profile is fine. The interesting thing is that depending on the probe you're using, depending on how many test batches you're taking, depending on the stability of your computer and the software running, you can run into problems by doing profiles that are too long. In fact, typically with these things, if you take too many measurements, you can actually start inducing things like banding as the panel or as the LUT tries to overcorrect for small errors. And what helps a lot with that is having tetrahedral interpolation, which, by the way, all DM series with the latest firmware now have. So tetrahedral interpolation will give you much less chance of that happening. And also better probes. But if you have a probe that, if you measure the same patch 10 times and it gives you, a difference of 0.003 in the X or Y coordinate every time you measure, then probe variability from reading to reading can induce problems by taking too many readings. So sometimes spacing out readings more, taking less readings actually leads to a more pleasing visual result. So those are all things worth testing out. If my display in post did this off of a 6-minute cal, I would not waste the time doing a larger profile, even if I had the time to spare.
Copy that. Just to reiterate for everyone kind of curious, if you do a verification first and your results are coming in like this, I think Bram can agree that there's not really a need to calibrate.
Don't redo your cal. I mean, it's like updating software in the middle of a shoot. You're just asking for problems. So.
All right, let's get to some questions. Kyle Hoekstra, you had a quick question.
Hey, Bram. In CalMan, there's a feature that allows you to emulate your calibration before loading it up into the monitor. I found that the most time-consuming part for me, at least, is always having to load the LUT in, put all the settings back, and then rerun the verification. Using the Calman simulation, is that at all trustworthy, or is that just a waste of time and to always load it up before you do your verification?
No, it's a good general guide. It will most often not agree completely with the monitor, with the LUT loaded on the monitor, and that has to do with different internal LUT sizes, different interpolation. So you will almost never get the same exact readings, but if they're generally good in a virtual LUT, then they will most often be good applied as well. So it's a great little sanity check if you want to do the virtual LUT. I can see if, so with cube generator. So I should mention that that is entirely possible to do both in Calman and in Lightspace. So in Lightspace it's called active LUT, and in Calman it's called virtual LUT. And you can check your LUT result that way. So yeah, you can do that, and it's a valid approach. Just don't expect it to be the same. In fact, most times you'll find, specifically in the Calman iteration here, that the applied LUT will perform slightly better. So you should be good if your virtual is good enough, your applied should be even better.
Awesome. And then one quick question: when you're using DaVinci as your pattern generator, do you need to, or does the LUT interpolation setting inside Resolve affect
No.
the pattern generation?
No, it has no bearing. The one thing that will have a bearing due to rounding errors, if you want to really get down to the nitty gritty of it, is that it is ideal to run a 3G level A signal to the monitor and feed it 444 RGB. Since your RGB triplets are, your test patches are all defined as RGB triplets. So if you have an RGB signal, that's ideal. If you feed it a 422 YCBCR signal, you induce some rounding errors between that. It's not going to change your result massively. You know, you can get away with doing 422 all day. But if you're, you know, as I say, the saying lately has been chasing the delta E dragon. You know, if you want to make sure that everything's less than 1, then 444 RGB will give you a slight benefit versus doing YCBCR.
Thanks.
Awesome. Sim Cohen. Scene. Let's make sure you unmute yourself, Scene.
Can you hear me now?
Yeah.
Okay, cool. So yeah, my question, hey, Bram.
Hey.
Just going back to the Judd modified question from earlier. You kind of went through it fast in Calman, but you mentioned where you would put that in, and it looked like you didn't do a Judd modified for that.
I didn't, yeah. So I was using an LCD, so it wouldn't have made sense to do it on this one. But yeah.
But isn't there also on the, at least on the CM and DM series, a separate menu for that within the monitor that you can do?
Yeah. So that is a great question. So you can do it 2 ways, right? And we specify this in the manual, I believe, as well. So you can target Judd modified directly in your LUT. And if Judd modified had been an available target, or if custom targets were available in Lightspace and Calman back when we first started doing all of this, this would be almost 8 years ago now, then we probably would never have added that menu selection. The reason we added the menu selection was because most probes and most calibration software at the time didn't have those targets pre-programmed in. It was too early. So what the menu selection allows you to do, again, thanks to the linearity of the OLED panels, of the RGB top emission OLED panels, is that we were able to employ that modification after a standard, you know, plain Jane vanilla 1931 CMF calibration. So you can use that menu selection and it will alter the white point. Mathematically, it will transform from a perfect D65 cal, if you can do that, to the Judd modified white point without you having to do anything special in your calibration software. You can also actually targeted directly in the calibration software, and arguably that might be more accurate these days to be able to target that very specifically by doing actual readings and building your LUT for those specific targets. The one thing you have to be careful of, as we've all come to say, is don't double JUD. If you double JUD, you can get yourself in trouble. So you just have to know which one to do. But if you were doing a cal for JUD, you would just select that as your target instead of Rec 709. And just to be clear on where you would do that, so if I go back to sharing here, and I've got my color space target, you can actually do like Rec 709 JUD. You can create your own new one. So you can basically type in what you want your red, green, blue, chromaticity coordinates to be. You can select the light point. You can select the EOTF formula as a target, and it will calibrate for those things within the program. So there's multiple approaches. You can, again, do it kind of either way. This as an alternative to what, so some of our competitors don't do 3D LUT based cal, they only do white point calibration. So the early advice was to do the offset at the probe level. So you would actually offset your probe readings. And as we talked about, that works great if you're only offsetting white and only measuring white. But if you're trying to do a volumetric profile on cal, that's really dangerous to do it at the probe level because it would affect your readings of red and green and blue and everything else, and your cal would be quite off if you did it as a singular, subtract this amount and this amount from all the XY readings. That's why we don't advise doing it at the probe level at all, ever. It's just a bad practice if you're doing volumetric calibration of your monitor. You can do a alternate CMF if you want on the probe, but you should not do just kind of blunt instrument XY plus minus of every reading.
And then on that note, you would also want to make sure that the JUD modified menu setting was off before you did the calibration, right? Because that would.
Yeah, you want to make sure it's off if you are. And so one interesting thing that we've did several years ago is we added one 3D LUT memory position that's called R709JM. And so you can save your file as jm.cfe instead of rec709.cfe. And if you save it as jm.cfe and put it in that position, it actually doesn't allow you to select JUD as a menu toggle. It actually automatically grays it out. So that's a good way to prevent the dreaded double JUD, is to, if you're calibrating directly for that, save into the jm.cfe position, and it will lock out that option on the menu.
Cool. And then you kind of covered a lot of this already, but when you're attempting to do HDR calibrations, it's a whole other set of settings within the software in order to achieve that, right? You basically have to know the display technology, make there's also different HDR technologies. So you have to set things very explicitly. Like, is there, maybe it's off topic, but how do you go through like an HDR workflow within this?
So we'd have to go back to Lightspace to show that, but basically you select PQ as your target, and you profile very much like we did. You'd obviously want to put the monitor in its high luminance mode to start, and then depending on the approach you're using, either build that back 1D gamma or back 1D PQ response, and then do your volumetric cal and just target it. The important thing with targeting in Lightspace, with targeting the PQ LUT, is that you have to type in what the max luminance of the display is. Otherwise, it will calibrate it as if though the display is doing 10,000 nits, and it's not. So your result will be scaled and it won't be correct. If you're interested, I can show you that real quick by switching to Lightspace. I don't know if we're getting too off topic or if you guys are cool with me showing you that real quick.
Might as well.
And you mentioned CalMan is not going to have that feature until later.
So right now, the only HDR calibration that I know of that they do is twofold, right? They do the kind of QC. We actually do a lot of our HDR QC with CalMan. It has some great Delta E ITP reporting. They're one of the first to implement that, and that is actually the new delta E metric used when doing validations for like Dolby Vision facility certification. So they have some great tools for that. You can do manual cal on some displays. You can do manual tweaks on our displays. And they also, on some consumer devices, I believe, do matrix plus 1D LUT. But what they don't do right now is 3D LUT-based cal for PQ targets. They don't advise that, but I have it on very good authority from them that that is coming. It's something they want to do. But right now, we do that actually within Lightspace. So I'll quickly switch back to Lightspace and just show how that works. And still sharing my screen, good. So I won't actually have to profile, we'll just kind of show how this works in theory. So again, because professional displays are supposed to hard clip at their peak luminance, there's no tone mapping, there's no roll off. They're supposed to just follow PQ exactly and then hard clip at the max level. When you are actually building your 3D lookup table for that, you have to actually select that as part of your LUT building process. Let's see if I can find that real quick. So let me just see if I have one saved here. So give me just a second to find a sample. There we go. Okay, so what you would actually do is so here you're going to select your target. So let's say we want to do PQ, P3, D65. And then I'm going to select a profile I did of a test monitor that we had in here. And what you're going to see here is the maximum measured luminance at the time for that display. So it's 949 nits. So what we want to do here in this EOTF nits area is we actually want to type in that same number, 949. And then we want to create our lookup table with that. If you don't type in this number, it will try to target 10,000 nits in the LUT, and that will give you a poor result. So I'll let that run for a second, but basically that's the additional step you have to take when doing those 3D LUT-based cals is you have to tell it where that hard clip point is, where you want the LUT to basically cap itself. And that's what you'll get by typing in that number. This, because it's a PQ LUT, will take a little bit longer to generate. But when it's done, I'll be able to show you where that hard clip is taking place in the 3D lookup table. Now, interestingly, we talked about kind of being able to do like tone mapped 3D lookup tables for use on lower luminance displays on set. By actually clicking on the EOTF nits button, you'll have those options. That's where it's going to show you where you can start your roll off, where you can end your roll off. So it has some of those toggles for scaling and tone mapping to allow you to kind of mimic HDR behavior in lower luminance displays. So that's something worthwhile to look at if you're looking for something besides kind of the built-in settings on a DM series. If you want something a little fancier for, whether it's our monitors or 500 nit monitor or 600 nit monitor that you're dealing with, you can actually make those selections and toggles from within the program there. Sorry, this generating 3D LUTs for PQ takes a little bit longer. So maybe there's another question or follow-up question to that.
Yeah, can we sneak another question in while this is going in the background?
Yeah.
From somebody that typed in, for Sony PVM panels, is there a best practice for incorporating a LUT box for calibrating panels that can't store an internal LUT? I know that's technically your competitor, but you know,
No,
it's a question.
it's a valid question. I mean, you know, our sales pitch angle of it is that, you know, we love seeing that when there's a monitor that doesn't have built-in LUT support that has a LUT attached to it simply for calibration purposes. That's a big win for us, because that, you know, having a open calibration architecture, being able to work with Lightspace and Calman and, you know, user-generated 3D lookup tables from, you know, home-brewed applications. We're all about that. So we like seeing those types of things. But all you would do is you'd put it in this widest gamut mode. So what you're trying to do is approach either native color gamut, if that's an available selection, or if you can't do native color gamut, just the widest gamut. So if there's a P3 selection, do that. If there's a wide selection, do that. And then you profile the display, and then you generate your LUT like you normally would and load it onto the box IO. Or, you know, honestly, if you're just using it for calibration, not that we wouldn't love you to use a box IO, but they're cheaper LUT boxes. If you just need a static LUT, you can do that. Or if you're really on a tight budget, you can load display LUTs even within Resolve directly. So those are all possibilities.
Do that. Chris Bolton, you're up.
It's kind of a three-part question, and actually, I'm just going to ask the question that Danny just asked on the chat.
Sure.
Was, does Sony have published numbers for offsets somewhere? Any idea about that?
When you say offsets, you mean for the probe offsets?
Yeah.
Yeah. I can tell them to you by doing the math, because all it is they're recommending that you use JUD, right? So it's going to be, you take 3127 and then you subtract 3067, and that gives you the offset amount. I think it's 0.011 and I forget.
If you download the Sony software and look at it, it actually says right in the software app what that is.
Yeah, 0.011 and point say 3127 minus.
They also have specific offsets for different probes that you're using too.
Yeah, that I'm a little, that's a little more dubious, but if you're using a Spectro, there would be kind of a set way to go. Now, the other thing is that there were 3 variations of top emission RGB OLED panels. Actually, there are more, but there were 3 variations of SPDs that I know of. And for each one of those, there might be slightly different targets to get you to JUD modified value that would equal what the CRT would have measured.
So my questions were the peak luminance you had in that PQ option in the calibration software. Where was that value derived from? Is that just from a previous calibration, or how was that derived?
You mean where it said maximum luminance?
Yeah.
Yeah. That was a pre-release 311K that we did that only did 949 nits. New ones uncalibrated do closer to 1050 to 1100 nits, and then calibrated right around 1000 nits. But yeah, that's just the measured value basically. So what's cool is as you select your, actually go back to the screen share here. So as you select the profile that you did here, it will actually automatically pull the maximum measured luminance value. And you can type in that figure right here. Now that is assuming this is the figure you get and it measures D65. So again, with us, because we're using a back 1D LUT to establish baseline white balance and EOTF, that will be D65. But if you were doing like a WOLED natively without a back 1D LUT would be like 10,000K. So you have to actually probably type in a lower number, and that's a little bit of a try and examine, see what works, because color temperature changes in 3D LUT based calibration are always going to be subtractive, right? So you're going to lose luminance. So here we won't lose much of any luminance because we're staying D65. But if I was also trying to do a color temperature shift, then I might have to spare 50 nits to go from 10,000 K to a lower color temperature. So that's a little bit, trial and error to see what works if you're not already at D65. But if you're already at D65, like you would be with any of our monitors, this won't be an issue, and you can just type in the measured number.
Right. And then the second question was, is there a way to use the Box.io yet as a test pattern generator?
There is. The only reason I'm not showing it is that that's just not as common of a method, but Box.io has TPG built in, and you can actually connect it directly in both CalMan and Lightspace as a test pattern generator source. So I won't be able to do it until this finishes building my LUT, but I will. I can show that. But basically, you just connect to it as like we did in CalMan, connecting to Resolve by typing in an IP address. You type in the IP address of the Box.io, tell it that that's your TPG source. And what's kind of neat about that is you can use Box.io as either a standalone TPG or you can use it as a TPG and your actual LUT device. So and one thing that we added at the request of both Portrait and Light Illusion, and this was probably a couple of years ago, is the ability to have the LUTs active in the TPG mode as well. So you can validate your LUTs on the actual device without having to use an external source. So it'll generate the LUT and the TPG in the correct order so that you can actually validate the result on device without having to use, again, a different source.
Right. Yeah, I have a spare Box.io Lite kicking around that I could use for that. So
yeah, they work great for that. The cool thing with that is you can also, with our TPG, select whether you're getting 8, 10, or 12-bit output. 12-bit TPG is typically otherwise difficult to get out of other devices. You can, yeah, I mean, it's pretty straightforward, but yeah, it's a great little extra device if you don't have a deck link or a mini monitor or something like that laying around for TPG.
Cool.
Yeah.
Jordan Livingston,
you're
you're
still
up.
churning, unfortunately. So, but go ahead.
Hey, Brom, it's Jordan.
Yeah.
I have this super quick question about the screen you have up right now, and then I have my actual question. But
sure.
Where are you getting that profile from? Is that something that you provide for the monitors that you manufacture, or did you have to generate that profile?
Sorry, I don't understand the question. Which profile? Sorry.
When you selected the destination color space, and then it told you that your maximum luminance value was 9.
Oh, that was just a profile it did. So all your profiles will show up in that destination list. So that's all it is previous profile. So whatever monitor you have, if you have a DM250, DM240, and you do your profile. So the one that we did earlier, I called it ZDITWIT. So ZDITWIT would be in that list. And
so that is the profile that you generated.
That's just a profile that we took of the display in its native state. So
gotcha.
Destination, again, is always the measured device. Source is always the incoming signal, so to speak. And what color space you're supposed to be operating in. The source versus destination thing kind of throws people off sometimes. Just remember destination is your monitor.
Gotcha. So my broader question is this. Like, I'll often have a couple of the same model of monitor, like I might have a couple DM250s or DM240s, but they're all different ages. And so we'll run calibration on them and they'll all come in within acceptable tolerance levels, but perceptually they don't really truly match. So what would you suggest in that situation?
So there's a couple things you can do depending on the probes you're using, and one of them that works quite well is averaging readings. So one thing to remember about probes is that if you take consecutive readings on a probe of the same exact patch, even though the patch isn't changing colors, you might get slightly different XY values. And probe repeatability is usually on the order of 0.0015 or something like that for X or Y. And that variability can actually cause changes. So one thing you can do is do averaging of readings. So if you do like 3 exposures instead of 1, then you'll get better average readings. And if you do that across multiple displays, you tend to get a more, because you're kind of canceling out the variability of the probe. So that's one thing you can do to improve it. The other thing you can always do is you can, if you have a master display that you like the way it's set up, you can profile that and have that be your target instead of a color space. So if you're targeting the same color space though on the same type of display like Rec 709 on multiple DM250s or DM240s, those should all line up pretty well, and you're probably more looking at probe variability as the culprit if your measured results are, you know, slightly higher or lower when you're done. The other thing you can do is larger profiles. That may help, but I would try the exposure multiplier is what's called with CR100, or the number of samples is what it's called in Calman. So you can take like 3 samples per read, or 4 samples or 5 samples, and that helps a lot with consistency and repeatability.
Where would you go to set that master monitor, like let's call it your A camera monitor, as the target?
So it basically is the profile that you did. So that profile would show up instead of as your destination. You would have that as your. So once it's calibrated, you profile it again, and you set that as your source, and then that source becomes your target color space.
Cool. Thank you.
Yeah, no problem. And I am going to kill this because I did something wrong, obviously, because it's still churning. So let me.
Do you want to move on, Brom, to the
Yes.
rest, like the devices, box AOs, monitors, probes, etc., and we'll come back to that.
Yeah, let me
part.
let me just kill this first, and then so I can actually open other things if I need to.
We can talk about the mother of all LUT boxes that is now super tiny. It runs off a 12-volt, handles 4 cameras, and it's under $200.
No.
Take my money.
And CFP integration.
Yeah, that's a big one.
The other CFE.
The other CFE.
Yeah, I mean, so just generally speaking, this is not specifics on any products or partners, but one thing we're looking to do on upcoming LUT-based hardware is the ability to basically run third-party code on it. So we're, at least at a conceptual level, extremely open to partnerships. There's my statement.
We like that statement.
Yeah.
Like that statement a lot.
It matches up with what the color front guys were talking about yesterday.
Let's see if I can.
Do you want to start talking about Boxeo and anything that you can share, Brom?
Yeah, so real quick, kind of show what a PQ LUT might look like. So this is kind of what the resulting EOTF would look like for potential PQ LUT, but this is one that actually goes to 10,000 nits. So we would see it clamp a lot earlier if we were on a lower luminance display. So if we were on like a 1,000 nit display, you would probably see this clamp right around this area right here. So just wanted to show an example of how that EOTF looks different when you build a PQ LUT. Cool. And then figure out how to do this again. Struggle is real sometimes. All right, here. This is view. All right, sorry. So the one last question I want to try to show real quick before we get into those other things. Sorry. It's just a clear answer on that. If you were to profile one monitor as kind of a master monitor. And yeah, okay, so destination is the display profile we did, right? And if I was going to use another monitor's result, so validation result, so I could do, this is the monitor profile we did. This was another monitor that I validated. I like the calibration of that. I want this to be my target instead of just like Rec 709, for example. So this is useful if you have someone who's, if you hand your monitor to a DP and the DP's decided to fiddle with the knobs and says, no, now I like it, and this is how I want it to look. You can actually profile that display and have an objective target to calibrate everything else to make them all look the same. So that's how you would do that with the source and destination targets.
That doesn't
make
sound
sense?
wise.
It's a god awful idea, but sometimes path of least resistance. All right.
Really wish you didn't show us that. Now that's gonna live forever in this video.
Yeah. Anyway, sorry. So there were other questions. Let me answer those. I am horrible at doing two things at once.
I think we're gonna move on to the devices.
Yeah, sure.
Any news about monitors, new monitors, box AOs, etc.?
You're gonna see us hold off a little bit with everything that's kind of going on. We're not gonna rush things out quite yet, but stay tuned for just a little bit later this year. There should be a few different announcements. Things that we have done, of course, are all the XM310K work, which was important not just for the algorithms that we developed there, but also something to keep in mind is that a lot of the code base and stuff we've been working on with the XM series feeds into what we're doing with future LUT devices. So a lot of that work kind of funnels into two different directions, but there is stuff coming. I can't say too much, but there's stuff. We definitely recognize the need for 4K capable LUT boxes, for multi-channel capable LUT boxes, for LUT boxes that can support third-party apps and on device perhaps, and also for much larger lookup tables. So we're building platforms that should be very robust to support a lot of advanced processing coming up pretty shortly.
Copy. Any questions, guys? Is there anything you can show us, by the way? Or no?
No, not hardware-wise stuff.
All right. Kyle Hoekstra, you're up.
Any pathway to have not just still capture that updates every couple frames, but actual full video capture, so we can get rid of those Blackmagic capture cards?
Not on Box.io. Well, wait. Let me rephrase that. Do you need it to be uncompressed?
Not at all.
Okay. Maybe.
Come on.
But yeah, obviously the big issue with the big difference now is that the frame captures we're doing at this point. So while you might just be getting a small thumbnail view in live grade, the important thing to remember is that every time you do a still frame capture in live grade from a Box.io device, you're actually getting a fully uncompressed full resolution frame. Which is why doing them fast enough to do video is not possible. Now, you can imagine that if you do some sort of sampling or compression where you're not getting full res frames, faster update speeds may be quite possible. So yeah, that's that's certainly been discussed. Yeah.
Lee had a question. At CES, LG came out with a 48-inch OLED. He plans on making a 48-inch XM monitor.
Well, not with that panel, no. So we make the 55 and 65 to address what I think is a pretty real world need in post. We jumped into that, and they are very useful for certain applications. The 48-inch panel currently is not available to us, and the WOLED panels, honestly, on the professional side, we're seeing the demand on those taper off. So because of the large demand for HDR, I believe. So for clients who are doing SDR, it's an extremely popular monitor. For clients who just need HDR client preview, it's a really good option too. But then the thing that we as a company have to battle against is people using consumer sets for client and not willing to pay the premium for a mastering level monitor just for client preview. So while it remains a healthy kind of product line for us for people doing SDR mastering, I think what people are looking for now is more HDR tuned or HDR geared displays. So our focus is really more on those technologies, is things that can handle HDR a little bit better from a mastering perspective.
Chris Bolton, you're up.
I'd just like to say, if any way to get frame grabs off a box I know faster than about 2 seconds would be greatly appreciated.
Yeah, that's
all.
So one thing I can say is that over the last, as mentioned, we wrapped up that pretty massive project on XM backlight algorithms. That took up a lot of our development time. It was important for future products and important to make the XM310K better as well. But we've got more time on our hands now. I think everybody has more time on their hands now, but we have more resources that we can put towards some of these.
Curtis Abbott. Make sure you unmute yourself, Curtis.
Yeah, I keep getting into the thing, whatever. So without reviewing any future plans, do you think we all need to think about moving towards, the 30-inch monitors, or will we see something coming with 24-inch monitors? I remember a while ago, Sony released that 24-inch. Sorry, we're not referring to, there was a certain 24-inch monitor that was global dimming that wasn't so great. Do you think the days of 24 inches are going away, or will we see,
No,
something coming?
So we definitely don't think the days of 24s are going away. I mean, one of our best-selling monitors is still our DM240 for just a really affordable HD monitor. We think we know that size and form factor make a lot of sense. The challenge we have is that part of the reason people want smaller on the production side, at least, is because of the increased portability. But on the post side, where that's an important part of our calculations in terms of what the demand's going to be like, it's not really much less expensive to make. If we want to make something that competes with a 311K, then doing that in a 24-inch size, it's like there's no, our cost savings is mostly freight. So it's difficult to do something at that level. I think what you're going to see a ton of, this is my prediction, not just for FSI, but what you're going to see from a lot of different companies, is precisely the both full array local dimming and the zone backlight options, because people are trying to strike a balance between power consumption, form factor, high luminance capability, without going to something hyper expensive like these, $30,000 plus light modulating cell layer panels. One huge issue that I think we're going to run into is that in post, I think LMCL, the light modulating cell layer, is going to be those options really only in the 30-inch plus sizes. So the smaller sizes are going to be different from what post is preferring. So I think that's what's going to happen is it's going to force some of the productions, especially higher budget productions, to also use 30-inch light modulating cell layer, even though the form factor and price aren't ideal, but just for that consistency with post, because the 24-inch monitors are more likely going to be zoned or global dimming options if you want something that's HDR capable. So unfortunately that, yes, there will be options smaller than 30-inch. They just won't be the same thing that post overwhelmingly is falling in love with. And in fact, you may have some facilities that look at it kind of the opposite way and go, well, we're going to get like a 310K with a zone backlight, both because it's now more affordable that we have it on sale, and because it can do higher luminance, but also because it maybe looks a little bit more like what the people on production are using actually. So there's going to be a lot of weird discussions like that happening now, but for workflows where consistency between post and production are really important, I think this is going to be a really difficult discussion going forward because it's not going to be the same type of technologies.
Copy. Back to the Box.io question about compressed video, if that was even possible, or at the bare minimum, 1 frame per second recognized as a capture device in live grade.
Yeah. So yeah, those things probably are doable. I think what we would probably do, and there's no hard promises on this, but it would just be like a sampling every other, every 4th or every 8th pixel or something like that, and giving you a quick and dirty, smaller image that way. Actually doing proper compression, so to speak, would be for future hardware.
Got it. Shell delay.
Hey, this is a service question.
Sure.
Is worldwide, I realize DITs are a small percentage of monitor sales and service, but is there some way to conceptualize doing like a couple weeks on the East Coast and a couple weeks on the West Coast for service every year, or some way that we wouldn't have to send our monitors to Atlanta?
Yeah.
Alpharetta.
So one of my kind of, and this is maybe revealing a little bit more than it should, but one of my long-standing considerations, things that I've always wanted to do, is have something on the West Coast personally, and we've come dangerously close to that at times. The current situation kind of makes any of that downright impossible, but just so you know, that is something we've been thinking about a lot. Now, the other thing is we have moved to having, before all this quarantine business happened, we did have a salesperson essentially from FSI out in California, typically at least 1 week out of every month. The idea of having a support person out there, it's not a crazy idea, doing something similar. So that's something, once things get back to normal, we could look into that. We actually have a partner there that has offered us a potential co-located kind of space to do something like that. There's more on the calibration front, but maybe that's something we can explore with them once things get a little bit, more back to normal. For what it's worth, we see about 20% of our business, I think, from Southern California. So we know it's an important market. It's also just a hyper expensive market to operate in, as I know you all know. So, but yes, that's good feedback.
Awesome. Chris Bolton, you're next. Chris.
Sorry, my door all went off. So sort of back to sort of like someone about asking about, is you think 30 inches the future? Would you think that something like that could give you an equivalent of a 24-inch, but over a larger monitor where you could tile and have two 24-inch equivalent images on one monitor would make sense?
So like a 48-inch display basically, or
Yeah.
I mean, possibly. I think that might work against you in terms of trying to power that thing if it was for HDR. Power consumption and heat consumption and size of the displays become pretty real considerations at that sort of size level. So I think we can make something that's makes sense for post, but people already kind of complain about the logistics of getting like a 55-inch OLED on set. Anything besides OLED, like a light modulating cell layer panel or something like that, is going to be a pretty heavy beast. But yeah, it's perhaps is the best I can say, especially with the fact that, again, light modulating cell layer dual panel type monitors are probably mostly going to be found in that 30-inch, 30 to 65-inch is kind of the real world scalable range of that technology in terms of what's going to be available in the coming years.
So you just take a 48-inch and just cut the top and bottom off of it. It'd be great.
Yeah. So again, dissipating the heat, especially on light modulating cell layer, becomes an issue. There's a reason the chassis is as thick as it is. It acts as a giant heat sink, and the 31s are also the first. The 311K light modulating cell layer is also the first product we've ever made that has fans built in because of the amount of heat that it generates. Those are relatively quiet fans. They're large fans that turn at relatively low revolutions, but we've never had to put fans in something before, and we do on these because they do generate a good bit of heat. A 311K draws about 280 watts too, for what it's worth. So in terms of bringing it on set, that's another consideration. For those reasons, because of those practical aspects, not the performance aspects, again, I think that the zone backlights are just realistically something you're going to see a lot of in production environments in the coming years.
Copy. Quick question, Bram.
Yep.
Somebody's asking, is it possible to do the side-by-side or picture-in-picture that you guys do, but currently if you rotated the monitor 90 and have them top and bottom in the 90-degree portrait view, if you will?
It is not. And the other thing is get a sheet of paper and do the math on that. It's not that much bigger of an image. I know that seems really counterintuitive, but you're gaining maybe an inch or so on the diagonal on a 24. It's weirdly not as big as you would think. But there is no way to do it on the monitor now. It would, one, induce a delay, and two, we don't have a large enough frame buffer built in to be able to even support it with a delay if we wanted to.
Got it. Kyle Hoekstra, you're next.
Stupid comment. Anyway, I know heat and everything. My monitors already give off so much heat. Anyway, we could do like liquid cooling instead of fans.
Yeah, it doesn't make them any lighter to do that. But there are companies who've done that. I mean, they're, again, some of the premier monitors out there have both fans and liquid cooling. The thing that you'll find with a lot of the experimental displays that have been built in the past is that if they use liquid cooling, they're also using fans, so it doesn't really help your issue, so to speak. Certainly form factor is not going to get any sexier by doing that. I mean, it sounds cool.
Talk about the service.
Yeah. Yeah, we'll just have someone come, recharge the Freon and it'll be good.
There's a comment from the chat just to keep 12/24 volt support for monitors, especially in the HDR realm going forwards, which we know is a huge ask, but
Yeah, on the so we don't do it on the 310K and the 311K, again, because the 311K draws 280 watts and the 310K draws about 200 watts. So it's 12 volts, it's certainly difficult. But as we move into some of the smaller options I hinted at, then that's certainly something we'd love to do. I think realistically, again, you're going to find that mostly on zone backlight or global dimming options. Any of the light modulating cell layer units, because of the amount of power they draw and because of the sizes you're typically going to find those in, are probably going to be AC only for the time being. So,
Got it. Anything else you want to say, or any other questions, guys? Kind of wrapping this up.
Bram, real quick, do the monitors themselves have more processing power than the box IOs?
Which monitors?
Like the DM class.
So the DM series and a box IO have almost exactly the same amount of processing power. The big difference is that in terms of like LUT support and things like that, is that you have to remember that a series of lookup tables on the DM series monitors are reserved for the calibration LUTs. So your C LUTs are different from your look LUTs, but the DM series is kind of like a box IO in dual channel mode. Honestly, that's the processing hardware is almost the same. That's why you get look LUTs on the front end, which is basically like using our, which I don't know if anybody uses it, but it's like using the internal loop feature that we have on our box IO, where you can loop one input into two LUT channels. The LUT stacking feature, that's the name of it. Sorry.
All right. If there's nothing else, we can wrap it up.
Awesome. Thank you guys so much. A lot of fun.
Wait, well, it's one quick question. I didn't think I thought that was just a straight loop out on the Boxio. I didn't realize it was a LUT stacking feature.
So if you, I could show this real quick. Sorry.
Sure.
Share screen, and I'm going to go to Box.io that I have connected. And share screen. So if
I have a note for you after this too.
Yeah, no worries. So if you look at your Box.io here, and you look at the inputs, you can have input is SDI1, input is SDI2, or channel 2 output. So if I go to dual channel mode, so I can have channel 1 be my SDI input, and then, but I could also feed the channel 2 output into there. So I can actually feed, I can see, basically stack one LUT. Kind of the way to understand this is if you were using Box.io in dual channel mode, and you were going in SDI1, out the processed out, and then back into channel 2, and then out SDI2, you could do it that way with external cables. By doing the channel 2 output and the dual channel mode, we can stack those LUTs internally, so you only have to use one cable in and one cable out, but you can basically apply 2 LUTs in sequence, actually 6 LUTs in sequence. So front 1D, 3D, back 1D, front 1D, 3D, back 1D. So 6 LUTs in sequence, all with one cable in, one cable out of Box.io. So it's kind of a very limited use case scenario, but our thought process on that, and certainly going forward in other hardware, is that if you get into complex like ASUS type workflows, now this would be limited obviously because you only have 17-sided LUTs, but if you imagine a device that would have 33 or 65 or even larger size LUTs, you could have, you know, one LUT basically be your ODT, one be your RRT, one be your IDT, and you could separate all those out piecewise, but still have one cable in, one cable out of a device doing that. So,
holy smokes! Hey, Bram, while you have that open, could you click on the settings tab right there for the Box.io? Is it possible in the future where it says change network settings to make this more obvious that it's like once you change the IP address of the Box.io, when you go into this, it looks like that this is the actual address of the Box.io. It gets a little confusing. Granted, I know it now, but
I got you. So what you're saying is, if I've changed it to like 10.1.10.77, that this pre-populates into 10.1.10.77.
I've had a few people ask me which the real, it's just a simple thing that people get confused about, but I've had people get confused, you know?
Yes. No, that's good. I'll talk to, so the software guy who does the IPRU actually works out of Atlanta. So I'll talk to him tomorrow morning about that. Cool. Other questions?
No, I think we're good, man. Thank you so
Cool.
much.
No, thank you. I really
Thank you so
appreciate
much,
it,
you
guys.
guys, everybody.
Yeah. Cool. If anybody has other questions, feel free to give me a ring.
Awesome. Thanks, Brom.
Yep. See you guys.